Okay, can we start?
NAKAR is there.
Yes.
It's different. The
Good
schedule
morning.
changed.
Udi, good morning.
Good morning.
Let's continue your beautiful presentation.
Okay. So, can I continue?
Yes.
Okay. So let me remind you what we talked about yesterday. I added to my presentation a long list of papers. I put 3 different topics. There are many more on other topics, but this is a good start. So what we've seen yesterday is that during the propagation of the jet, here you see a different type of simulation. On the right, you see this is a density, and this is the energy per barrier. And I remind you, this is a jet here in the center. This is a collimation shock. This instability that we talked about yesterday, this is a head. And everything in this region, this is a cocoon. So material is ejected from the jet. I remind you, in this specific simulation, also in others, we just inject the jet. We put the jet by hand. We do not care about where it comes from. This jet, in this case, is hydrodynamic. The flow is going up to the shock, shocked once, continues up to the head, shocked second time, and then spills down to the cocoon. On the other hand, if we look at the material from the star or from the neutron star merger ejecta, then this high pressure here drives the shock. If we look at this, this is the shock, and this shock is moving towards the medium. At the end of the day, today we'll focus on the cocoon. Yesterday we talked about the jet. At the end of the day, we have this high pressure bubble, which is collimating the jet, which we call the cocoon, as I said. And we have two distinct regions, the inner cocoon and the outer cocoon. Let's start with the density. You can see that the density in the inner cocoon is much lower than the density in the outer cocoon. The density in the outer cocoon is basically reflecting the density in the star. So the outer cocoon is composed, or the medium. The outer cocoon is composed of material that was shocked in the medium. Density is only a factor of 7, depending on the equation of state, but between 4 and 7 compared to the external density. The inner cocoon, here it's much more complicated. Here the density is basically the density of the jet with some mixing. And mixing can take place in 3 locations. And the mixing here is again very important. I will talk about it in a second, why it is important. But let's talk about where the mixing is coming from. So one region where there is mixing is what I talked about yesterday. This is the interface between the jet and the inner cocoon. This mixing is affecting the jet strongly, but not the cocoon. So for the cocoon, we don't care about this mixing. Second location of mixing is here at the head. When material is going to the head and spilled sideways, there is a very strong mixing actually. And the third location of mixing is here in the interface between the inner and the outer cocoon. You can see all these regions here, you can see that there is mixing. Now, one of the problems with mixing is that we cannot model it analytically, and we can never really tell if the mixing that we see is in simulation is numerical or physical. What I can tell you is that in a large range of simulations using different codes, and in all of them reaching convergence, we see roughly the same pattern of mixing. And the pattern of mixing that we see is that if you can see it here better in energy per baryon. So you can see that the energy per baryon here in the jet is hundreds. And you have this, the jet remains largely unmixed or with some small mixing up to the head. And then this region here, you can see that the mixing already goes down to an energy per baryon of about unity. Energy per baryon of about unity is gamma if we let this material to expand and convert internal energy to kinetic energy, then we'll get a Lorentz factor of 1 or 2 or 3, something like that. And as we go down in the cocoon, you can see that the energy per baryon is increasing. It is decreasing, sorry, all the way up to the base. An energy of baryon of 0.01 correspond to its final velocity of 0.1 c, roughly. If we take this, again, taking the kinetic the internal energy and converting it to kinetic energy. And this is something that we see in all simulations. So the head is mixing the jet, regardless of what is the initial Lorentz factor of the jet. The mixing in the cocoon brings the material here to be mildly relativistic in temperature. And so the random motion is with a Lorentz factor of about 2 or 3. And there is a continuous mixing along the interface with the outer cocoon. So at the base, material which is spending longer in the cocoon, which is a material closer to the base of the jet, is more mixed. Okay. And why is it important? This is important because what we are going to discuss now is the emission that we are going to see from this cocoon after the breakout. I remind you that after the jet is breaking out, so we have here the jet is breaking out, and once it's breaking out, of course, the cocoon is also breaking out. Okay, so this is from I didn't put here this is from a paper with Tsvi PIRAN that Tsvi and I wrote in 2017, where we give analytic prediction towards the emission from the cocoon will be. And you can see that the jet is producing the GRB. Let's forget about it. It's not for this talk. It's unimportant for this talk. And the inner cocoon and the outer cocoon are both going out. The difference between them is that the inner cocoon, we have much higher energy per baryon. So the material in the inner cocoon is escaping and accelerating roughly to the thermal energy. So the material going from the inner cocoon, the fastest material will get up to a Lorentz factor of about 3. And then we'll get material going all the way from Lorentz factor of 3, which is the one that is escaping first, or up to a Lorentz factor of about 0.1, which is the Lorentz factor, sorry, not Lorentz factor, velocity of 0.1 c, which is a material which is escaping from the base. And this material which is escaping from the inner cocoon is also escaping, it's not spherical. It will escape up to some opening angle of, let's say, half a radian, maybe 1 radian, something like that. Material from the outer cocoon is slower. This material is spinning sideways because of the pressure. It's producing roughly spherical outflow. And the typical velocity of this outer cocoon, is the same velocity as the shock that was propagating into the star. And this is also roughly 0.1 c. Okay. So now the question, we have these ingredients. I remind you again, we have an ultra-relativistic jet in a very narrow angle. We have mildly relativistic outflow in slightly larger angle. And we have sub-relativistic outflow in roughly isotropic. If we look at the amount of energy, then all the energy that was, I remind you that as long as the jet was propagating, all the energy that was launched into the jet basically went through the head and spilled sideways. So the energy in the cocoon is equal to the energy that was deposited, that was launched into the jet during the propagation. Now, if the propagation time is about 10 seconds in a long GRBs, as we seen yesterday, then and the luminosity of the jet is roughly 10 to the 50 ergs per second, so we get about 10 to the 51 ergs in this cocoon. This is comparable in energy to the energy that we have in the burst itself. So the jet carries about 10 to the 51 ergs. The cocoon will have about 10 to the 51 ergs. And if we look at the distribution of energy between the cocoon, the inner cocoon and the outer cocoon, then the pressure is constant. So the energy is proportional to the volume of each of the components. The volume is roughly comparable. So the energy will have roughly 5 times 10 to the 50 or comparable energy to the jet we'll have in the inner cocoon and comparable energy we'll have in the outer cocoon. So altogether, we get a distribution of energy which is roughly uniform in log space of gamma beta. So comparable energy in ultra-relativistic velocity, comparable energy in multi-relativistic velocity, and comparable energy in sub-relativistic, roughly 0.1 C. Okay, and the question is what will be the emission from these components. So the emission is basically what we call cooling emission. Why do we call it cooling emission? Because we have material which is expanding. The optical depth in this material is very high. Very high optical depth implies that it takes time for the photons to diffuse. And roughly speaking, photons escapes from the outflow when the optical depth to infinity is comparable to c divided by the velocity of this specific outflow. So in the multi-relativistic part, the radiation escapes when the optical depth drops to unity. In the sub-relativistic 0.1 C material, the emission escapes, the radiation escapes when the optical depth is roughly 10. Now, up to the point where the radiation escapes, it suffers adiabatic cooling. So if we want to calculate what will be the emission that we observe, what we need to do is what is the initial radius of the material, what is the initial energy density and temperature of this material, and then we follow this material through the expansion. We account for adiabatic losses in the radiation and the cooling of the radiation, and then when it escapes, we know how much, we know roughly what is the time that the optical depth drop to C over V, and we can find what will be the emission, when we will see most of the light, what will be the temperature, and how much energy we are going to observe. So if we look at the Newtonian emission, what we need to know two things basically. We need to know what is the mass, what is the energy. This is giving us the velocity, and if we have the initial volume that this material occupied, we can calculate everything. So the mass is roughly the mass is roughly the mass of the star multiplied by the opening angle of the jet. The reason that it's multiplied by the opening angle of the jet square is the fact that the size of this cocoon, if I look, for example, no, you cannot see it here. But if I look at the size of this cocoon, the angle, for example, from here to here, if I look at this angle is comparable to the initial angle of the jet. This is one of the properties of cocoon, that the size of the cocoon is roughly the size corresponding to the opening angle of the jet when it is injected. So, for example, if the jet is 0.1 radian, then the volume that is occupied by the cocoon is roughly the volume of the star multiplied by 0.1 square divided by 2. If we talk about a star of about 10 solar masses and an opening angle of about 10 degrees, we get that the mass in this cocoon, in the outer cocoon, is about 0.1 solar masses. The energy, as I said before, is comparable to the energy in the jet, roughly 10 to the 51. Here I took a slightly stronger jet, so it's almost 10 to the 52, but this is because of the parameter that I chosen. And the velocity is simply the ratio of the energy divided by the mass, roughly, which is about 0.1 C, as I said before. So altogether, once we have that, we can estimate the emission. I will show you the estimates later. No, here is the estimate. So as I said, we look for the time where the optical depth is equal to C over V. The optical depth is simply the mass multiplied by the opacity divided by the radius square. The radius is V times T because everything is expanding with roughly a constant velocity, all this material. So we can find what is the time where the radiation escapes. This is roughly 1 day. So we expect the energy deposited in the outer cocoon to radiate roughly on a time scale of a day. What will be the luminosity? The luminosity will be the energy in the cocoon, the initial energy, after accounting for adiabatic losses. Adiabatic losses are simply goes like the volume of the initial volume of the cocoon to the power 1/3 divided by the radius of the, so the initial volume divided by the volume at the time that the emission escapes to the 1/3, and so this is the energy that is of the radiation, and divided by the time, this time we get the luminosity. So we get a luminosity of about 10 to the 42 ergs per second. 10 to the 42 ergs per second is roughly the luminosity of a supernova. Okay, typical supernova, the luminosity is between 10 to the for type 2Ps, type 2, which are the most common supernovae, core collapse supernovae, the luminosity is roughly 10 to the 42 ergs. The difference is that in supernovae, these 10 to the 42 ergs are radiated for about 100 days, while in cocoon emission from long GRBs, the emission is over 1 day. So we expect to have a short-lived, relatively bright emission, and the temperature is about 9,000 degrees, very, very comfortable for observation in the optical. Okay, so the conclusion is that each long GRB is expected to be accompanied by a transient with a time scale of 1 day, temperature, which is in the optical band, and luminosity, which is comparable to the luminosity of the supernova. It, of course, will fade rather quickly. Yes, it will rise over 1 day and then fall, or it will even rise faster than that. So, what I wanted to say. Oh yes, one important thing is, of course, if the jet is pointing towards us, then the emission from the jet is much brighter. We know that on time scale of 1 day, the afterglow, which is a result of the shock that the jet is driving into the external medium, typical luminosity is about 10 to the 45 ergs, 10 to the 44 ergs per second. So we are not going to see this emission if the jet is pointing towards us. But this emission is spherical. So we expect to have this type of transients also in region, also when we have GRBs which are not pointing towards us, and we know that we have about 100 times more for each GRB that is pointing towards us, is about 100 GRBs which are pointing away from us. So in principle, this is a prediction for a type of short-lived optical transient, which is expected to be observed once we will be able to cover a fraction of the sky which is large enough. Okay, the way to identify that this is indeed a cocoon emission from GRBs is to continue and observe this location, and we expect that after several months, the radio emission of the afterglow will become roughly spherical, and we'll be able to see the late radio afterglow of this GRB. Today, we didn't see any such transient. Looking at the observations of surveys, it is not very surprising. Okay, so this is the emission from the outer cocoon. What is the prediction for the emission from the inner cocoon? And I will start with a prediction of something that we actually do not see. I told you that the mixing that we see in the simulations is we can never be sure if this is numerical or physical. So let's assume for a second that there is no mixing for the inner cocoon at all. Okay, so we have material going from the jet, spilled sideways, no mixing at all. So the energy per baryon in this inner cocoon is basically the same as was in the jet. So 100, 200, 500. And then you can ask, what will be the emission from the breakout, from the expansion of this inner cocoon? So if you want to take a toy model, a toy physics model, we can have the following model. We have the star, we take a cylinder within the star, we fill this cylinder, the size of the cylinder is the opening angle of this cylinder is the opening angle of the jet. We fill this cylinder with energy roughly 10 to the 51 ergs, and material with energy per baryon of about 500 mass of the proton C square. And so we have some initial temperature, and we let this material escaping out and radiating, cooling emission. Basically, what will happen is that the material which is at rest will start accelerating, and basically we'll have a version of the fireball model with some baryonic pollution, and it's possible to calculate what will be the emission from this baryon, from this fireball. And it turns out that the emission that we will see will be very bright and in principle should have been seen in gamma rays. So the temperature that we are going to see is roughly 100 Kelvin. The time is over seconds, and the luminosity is about 10 to the 55, 1 ergs per second in this region. So this is type of signal that, and it should be roughly thermal. So this is a type of signal that you should have seen from GRBs over an angle which is larger than the jet itself. So it should be more frequent than regular GRBs, and it should be easily detectable with the gamma ray detector. So if there would have been no mixing for the jet material as it makes its way to the inner cocoon, we should have seen this type of flashes, and we don't. So this is an observational confirmation that the jet material which is going to the cocoon is actually mixed. So now let's ask ourselves, assuming that the simulations are correct and that we indeed have this mixing that brings the jet material to an energy per baryon, which is somewhere between 0.1 and 3 in units of proton mass C square. Then what do we expect to see? Yes, so I already talked about that. So this is a prediction of what we are going to see, where what you see here, this is the emission. This region here is the emission from the inner cocoon, okay? And this region here is the, this emission is from the outer cocoon. This is what I talked before. And this part of the emission is much more robust than what we have from the inner cocoon, because in the outer cocoon, this is independent of the mixing. In the inner cocoon, this is a prediction. So this emission here is coming, this part of the rising emission is coming from the relativistic part of the, no, sorry, this is not the relativistic. All this part is relativistic. All this part up to here, this is from the relativistic part of the emission, and this is from the Newtonian part of the emission. So I'm not going to get into the details exactly how we calculate it, but it's roughly similar to what I said before, calculating the radius where the emission is escaping the expanding material, accounting for adiabatic losses, and following and assuming thermalization. And you can see that the emission can be very bright. We can get up to luminosities of about 10 to the 43 ergs per second at early times. Again, but the duration here is very short. The duration here is about 1,000 seconds. We didn't see it yet. We might be able to see it in the future. And this is roughly the emission that we expect from the cocoon itself. Any questions?
I have a questions. Are there any connection this cocoon picture with this short GRB, long GRB scenario, this description? Any connection between this cocoon and short and long GRB?
I'm not sure that I understand the question.
I mean, we know there's there are classification of long and short GRB.
Yes, we know that.
So yes, but I want to understand that
You
Can
want to
I
know, you want
clear-
to explain the difference between the cocoon and short and long GRBs?
yeah, there's some connection between these two, between
Okay.
these.
So I'm not sure if there is a connection, but both in long and in short GRBs, there is going to be a cocoon. Everything that I've shown you now, the predictions here, are for the cocoon emission in long GRBs. We have also predictions for the cocoon emission in short GRBs. I did not include it in this talk because I don't have enough time. But these predictions are slightly different, but not too much, in the sense that the idea, the way that the theoretical model which is used to calculate both of them is rather similar. The difference is the cocoon emission in short GRBs will be shorter in time because there is less mass, so the radiation escapes more quickly. We are talking about roughly an hour time scale after the merger, and the cocoon emission in short GRBs will have two components. One component is the cooling emission that I've shown here, and the second component is actually powered by the radioactive decay of the R process elements. So in cocoon emission from short GRBs, there is another ingredient which needed to be taken into account. Altogether, we expect the cocoon emission to possibly dominate the emission in short GRBs over time scales of hours. And there is a reasonable chance that we'll detect in the future because we're going to have triggers from the gravitational waves. We expect to be able to observe the region of the merger within hopefully even much less than an hour, and we'll be able to distinguish cocoon emission from the emission of the bulk. For example, the emission of the bulk is expected to rise with a duration of about half a day to 1 day, while the emission from the cocoon is expecting to rise over a duration of about an hour. So there are several different predictions from early emission from neutron star mergers. One of them is the cocoon, another one, for example, is free neutrons. So there are several competing mechanisms for early emission. One of them is cocoon emission from short GRBs, and hopefully we'll be able to detect and maybe even tell the difference between this model and others, although we'll have to wait and see. Did I answer your question?
May I intervene a moment?
Yes, sure.
And Udi, very nice presentation. And let me, we have some important result, and we are trying to be ready to present some of them in the next days. But let me first point out that we hope also to have the presence of Luca, because all the work you have done can fit the very high quality data that Luca Izzo has discovered in his very important source. And of course, you have the great advantage with your simulation to be able to fit also the Luca data. But the difference between your approach and our approach has to do with the very early part of the cocoon. And of course, even in the reference that you have given, you have inserted there all the physics about the jets, which are not part of your presentation. You just assume to be a jet with so much energy which can fit your data, but you don't enter into that issue, if I understand correctly.
Yes, I understand correctly.
Okay, we enter in that issue. And I think we have what I consider very fundamental results. And we will try to do our best to present as much as possible. But let me tell you that this problem about the jet and the presence of a new neutron star spinning is very crucial. And fortunately, we have a beautiful result is 171205 a beautiful result in 1908-29A, which is now accepted in APJ, and is a prototype, more energetic than the Cocoon, but also with some presence of Cocoon in what we call a BDHN1. Now we have all sorts of problems. The paper is accepted with a glory comment by the editor, who insists in us making a press release. And I am insisting on the leading author of that, which Wang Yu. And we are battling about this situation because Wang Yu is recovering from this terrible sickness, but we hope very much that he will be able to present this result. Now, we have precise cases of this non-jet material. We have in BDHN1, in BDHN2, in BDHN3, and BDHN3 are the Cocoon. Therefore, we do our best to show you some, believe me, but we can only fight for the situation that we are people either in the hospital or recovering. Therefore, be patient, we will do our best, but let me tell you that the presence of this new neutron star can give an alternative, a much profound reason for the validity of your beautiful work, which is the reason I invited you. Let's try if we succeed in let you in giving more detail. But we have plenty of results. Therefore, we are fighting against the contingent situation. But believe me, you will like very much these results. I don't know if we will be able to present all of them, but at least to present one case very clear and ask you to think around that case 1908-29A to extrapolate to your source, to its source. Be patient, but we admire all the work that you have done. It fits perfectly and is extremely important. There are 3 levels in which the Cocoon can add, and of course it's in the weaker sources that you can see the best. In the other source you have other phenomena which make the situation not as clear. But the beauty of the weak source of ITSO and the beautiful data of Luca make your work much more important, in my opinion. Thank you again.
Thanks.
Can I ask questions? This picture you show the optical light from Cocoon cooling. Is I remember there are several keys in the optical afterglow show two bump, early bump and late bump. Your picture is similar to there's two bump light crash. I mean for the two bump light crash, optical light crash in the optical afterglow, usually we explain by the two component jet. My question is that scenario is consistent with your picture?
So in case in GRBs that are pointing towards, whenever we see the prompt emission, we know that the jet is pointing towards us. The afterglow is so much brighter that we are not expecting to see any. The emission from the cocoon is negligible. So I don't think that we can. It's fainter by 3 orders of magnitude. So in all the GRBs that we observe, when we see an afterglow following a prompt emission, I do not think that we have any chance to detect the signature of the cocoon. The advantage of the cocoon emission is that it's much wider, it's emitted over a much wider angle. So it will dominate the emission when the jet is pointing away from us.
Okay, thank you. Any questions? Any more questions? Okay, thank you for the last talk. Okay, let's move the next. Okay.
Next speaker, Tsvi.
I don't know who is like speaker. The schedule is correct or not? Because changes some.
Tsvi PIRAN is the next speaker.
I think I'm the next speaker.
Okay. The next speaker is Professor Tsvi PIRAN. Okay. Okay. You can start it.
Okay. Good morning. I will continue from the place where I stopped yesterday. And I reached my conclusions that on a very general ground, we must have a system in which we have an engine. There is a transport phase in which the energy is going out of the engine all the way to the outer region, and then the energy is emitted at the outer region and at large distances, and this is the conversion or emission region where we get to see the gamma rays that we observe. So this is the basic idea, and now I want to focus on the implication on the fact that there is a jet that has to pass through a star. So we know that long GRBs are associated with supernova. There is some evidence. These are two historical events. And in this case, it means that this transport of energy is more complicated. And Udi discussed it extensively because we have a jet which is produced here at the center of the star from the newborn black hole or newborn neutron star. And then this jet has to pass the star before it gets out to the region where the energy can be observed. So this is the question. Okay, so to do this, as Udi discussed, you have to drill, the jet has to drill through the stars. It slows down in this process and it takes time. This is that we heard the details from Udi, so I will not discuss it. This is a recent simulation that we have done, but we have seen many simulations like this. This is a comparable situation if you have here a magnetic jet rather than a regular jet. But the main point is that it takes time for the jet to cross the star. Similarly, if I want to make a hole here in this screen, it will take me some time to drill a hole in this screen and so on. And actually, a good friend of mine, of us, working on gamma ray bursts, told me that he did exactly this experiment. He made a drill in his hole, and then he hit a electric cable wire, and then there was a gamma ray burst because the whole house got on fire. So this was an experiment how to do a gamma ray burst. Don't try it. Don't try it. Anyway, this takes about 15 seconds for typical parameters. L ISO is 10 to the 51 ergs, theta of about 10 degrees, typical stellar size, radius, and mass. So, and the point is that, as Udi stressed, that the engine must be active all the time. If the engine stops before the jet gets out, we don't get a gamma ray burst, because the jet does not get out, all the energy is deposited into the cocoon. Now this leads to a very immediate prediction. This is the duration time distribution. T gamma is the duration of the gamma ray burst. T engine is the duration of activity of the engine. So there is a very simple rule that the duration of activity of the engine is the duration of the time TB to take to break out plus T gamma. So the probability to observe the burst with T gamma is equal to the probability the engine works T gamma plus TB. Now look what happens when T gamma is much smaller than TB. If T gamma is smaller than TB, then I can approximate this function as a constant, the probability for TB. If T gamma is much larger, then T gamma will be, the probability will be just the probability for the engine to work this duration. But for short duration, shorter than TB, the probability to have a burst of a given duration is constant. And to remind you, TB is about 10 seconds. So again, this is the picture here. This is the whole duration of the engine activity. TB is the time it takes to be in the star. We don't see anything at this time. T gamma is the time after.
Tsvi, excuse me, we lost you. We cannot hear you and we cannot see you. Anybody can call Tsvi just to try to restore the connection.
Can you hear me and see me now?
Yes, yes.
Okay.
Yes, we can see you now.
Okay, so I'll share the screen again. Share. I apologize for this problem. Okay, so this is the duration. This is the duration distribution, and regardless of the engine operation distribution, we will have a plateau at short durations. Now, you have seen this long and short distribution. These are the short bursts, these are the long bursts. And people take as a sharp cutoff at around 2 seconds to distinguish between long and short, but this is misleading. If you look at this graph, even by eye, you will expect that there will be some continuation here and some continuation here. But this graph is also misleading because this is a logarithmic plot and this is a linear plot. What happens if I plot it in log-log plot? This is the same graph. This is the duration distribution, and here you see this very clear plateau, the plateau that I was discussing. This time here, which is about 10 to 20 seconds, is the breakout time. What you see here is 3 detectors Batsy, Swift, and this is Swift, this is Batsy, this is Fermi. And you see that all of them has the breakout time at about the same time, which is about 10 seconds. So this is actually a confirmation of the fact that we do have jets propagating into stars, because we see direct evidence in this observation of the break time, and we can measure it. It is about 10 seconds. So this is the direct proof of the collapsar model. And it was a prediction, and it was verified here. Now, what about the other side? What about the end of the plateau? Why does the plateau does not go all the way to zero? It doesn't go all the way to zero because we have also non-collapsars. These are the short bursts. These are the non-collapsars. This is how they are seen in Swift and in other events. Here, in the long duration, we measure the real activity of the jet, of the engine. But the short durations here are the short one, and this is the plateau, which is an artifact of the fact that the jet goes through the star. Now, there is something interesting here, and the interesting thing here is that if you look at this extrapolation of the long duration phase, you see that I can extrapolate it down here. And this extrapolation suggests that there is a large number of failed collapsars, of jets which are produced and they do not manage to get out of the star. These are, you can call them failed GRBs, but actually what we expect is that these are the low luminosity GRBs. These are a subpopulation of the GRBs that are very low luminosity. They are we see only very few of them because they are weak, and we can see them only from short distances, but they are actually more frequent than regular GRBs.
Excuse me, show what is the red, what is the blue, and what is the green?
Oh, these are the three detectors. The red is Batsy, the blue is Fermi, and the yellow, green, the yellow is Fermi. So this just shows that we see the same phenomena in different detectors. It is not something that depends on the detector. What does depend on the detector is this point in which the end of the plateau on the short side, and I'll come back to it because this depends on the sensitivity of the detector. These events are the short bursts and genuine short bursts, I mean bursts which are non-collapsar in nature. These events are collapsars. And you can see here, for example, in Swift, that the collapsars goes all the way to less than 1 second. So if you take a burst of 1 second in Swift, it is more likely that it will be a collapsar than a genuine short GRB. Short in the sense of non-collapsar or coming from mergers. As a demonstration of what we see here, this is a movie here, and this is what let me explain what we see here. This is the also famous curve. This is here on the x-axis is of this insert is the duration, and the y-axis is the hardness. This population is short bursts, which are shorter and harder, and this population is the long bursts, which are longer and softer. And what I'll do is I take one detector, but I now reduce the threshold of hardness. And the prediction is that we get rid of the short burst, the plateau will become longer and longer and longer. So let's see this now. I'm reducing the hardness of the sample, and you will see I'm losing burst, but I'm losing mostly on the short side, and then the plateau becomes, you see, the plateau here goes almost all the way to zero, because, and all these are collapsars. All these are collapsars, and this is as if we don't have mergers in the universe, because we are working with very soft detector. So So this is the situation, and this is already, as I mentioned, that with the short bursts, the short bursts depend on the detector. I mean, what is non-merger depend on the detector, non-collapsar or merger depend on the detector. If you have a soft detector like Swift, then you have to take different threshold for division of between collapsars and non-collapsars. So, for example, there was enormous noise now in the system. Probably will be a Nature paper or whatever about 211211A, a long burst with a kilonova. There's nothing exciting about it. This long burst is not really a long burst. The main peak here is only 10 seconds. This is a very soft tail. You see, this is how it looks on a hard band. So here, most of the emission is coming here in the first 10 seconds, and the first 10 seconds are much harder than the rest. So this is the location of the burst if I take everything. If I take only the first two parts, it will move to here on the boundary between long and short. And in fact, if you look at the previous graphs and see that at 10 seconds, the probability of a burst to be a merger is about 10%. This was expected all the time, that these events will be identified when we look carefully at the data. This was a prediction from about 10 years ago, that some of the short bursts are some of the long bursts are mergers, and vice versa. Again, a second Nature paper, short GRB with a supernova. There is nothing surprising here. Again, this is a burst of 0.65 seconds in Swift. This is exactly on the boundary from point of view of Swift between collapsars and non-collapsars, and this is exactly what one should have expected. And actually, we don't have to have our very sophisticated analysis. You can even go all the way back to here and realize that there's nothing which will stop abruptly here. There will be a continuation of this population and continuation of this population. So this big excitement now about long bursts with a kilonova or a short burst with a supernova is just meaningless. This was a prediction. It was there. It was clear. It was just a nice verification of our prediction from about 10 years ago.
Longer.
And now,
why she should not come on Tuesday?
excuse me?
Yes, but
So Rufini, we can hear you.
excuse me.
Okay, so I already mentioned that there is a large population of this analysis suggests that many bursts do not manage, many events do not manage to have the jet propagating inside outside of the star. We suggest that these are the origin of the low luminosity GRBs. These events have isotropic energy much lower, 10 to the 48, 10 to the 49 ergs, about 2 or 3 orders of magnitude less than regular GRBs. A canonical one is 980425. It is very smooth burst, goes up and down in a single spike. It is very soft emission. And as I said, they are more numerous, but we don't see them. Some of them are associated with supernova. Most of them are associated with supernova. So what is this? This is the Cocoon breakout. This is the fade GRB, and this is the Cocoon breakout. And this suggestion goes very, very back. And this is what a simulation of this. Udi have shown his simulation. This is done by my postdoc Matteo Pais, and that's it. The jet was choked here, the jet disappeared around here. Yeah, let me begin from the beginning. You see the jet, I'll see it step by step. This is the beginning, the jet propagate. You can still see the jet. The jet is here along the axis. That's it. The jet disappeared. The jet was choked because the engine was stopped. And now we have only the cocoon. And now cocoon expands, breaks out. And this is what we see. And Udi and Nakar and Sari have very nice relationship. I don't know if Udi discussed it, that the breakout time is proportional to the breakout energy to the power half, and the breakout temperature to the minus 2.7. This is the some low luminosity GRBs. This is the breakout energy. This is the temperature. This is the observed breakout time. This is the breakout time estimated based on breakout energy and temperature. And the agreement is really beautiful. And from this, we can measure the breakout size and other factors of the system. So this is low luminosity GRBs, which I think should be interpreted in this way. And one sees many papers suggesting that low luminosity GRBs are GRBs with weak jets. I completely disagree with this kind of work. Low luminosity GRBs are not weak GRBs with weak jet. Low luminosity GRBs are events that did not manage to get out of the star. And I don't know if Udi mentioned that the Cocoon matter, which is expanding around, will have an effect on the supernova. We can see this in the absorption spectrum of the supernova, and in many cases it was already observed, and and this is observed by having high velocity material surrounding the supernova, and what we see is very deep absorption lines. This was seen already in 97EF, in supernova 97EF, where expansion velocity was seen with 60,000 kilometers per second, 0.2 C, and a lot of energy in this component. It was seen in 97. It was not understood what is going on for about 20 years until we suggested this. And more recently, there was a beautiful confirmation of our ideas by ESO when they observed the supernova 2017 IUK, which was associated with a low luminosity GRB 171205. So what they see is this absorptions line, which are changing absorptions line corresponding at the beginning to expansion velocity of 100,000 kilometers per second. This was a beautiful observation and a beautiful confirmation of our predictions. We were very excited to see these observations, and it is so nice that you make a prediction and then a couple of years later somebody comes and confirms this. Okay, so this is what I wanted to say about jets in stars, and it's a good time to ask if there are questions about this topic before we move to a second topic.
I have a question. How
Yes.
do we understand this collapse and merges, make this short and long GRB? How do you understand they are so?
What do you mean by how do we understand?
Means you provide some reasoning or explanation why the long, yes, I understand there's no distinct, there's a extension, there's no distinct two class. So, but you mentioned there's collapse and merge. So
Yes.
how do you understand this relation between collapse and merge with a short and long GRB?
This is because of the engine operating time. Many years ago, in about 2000, more than 20 years ago, I had a paper with Pawan Kumar and Ramesh Narayan, in which we suggest that the difference in duration is due to difference accretion time. In a short GRBs, in mergers, we believe that you form a small accretion disk around the central object. The accretion disk is small because there is not that much material involved. And if you have a small accretion disk, the typical time scale for this disk to accrete on the compact object is a few seconds or less, and this is how you get the short GRB. In the case of a collapsar, you have much more material. This is a collapse of a massive star. So you have a supply of possibly few solar masses of fallback material, and this fallback material falls on the accretion disk, and it continues to feed the much larger accretion disk. So we have much larger accretion disk, and this much larger accretion disk lives much longer, and this is how we get the long duration. The question why short GRBs are harder and why long GRBs are softer is an open question. I don't think, I've not seen a clear suggestion that explain this. So I agree that there are many open questions about GRBs. One of them is because in this context, this is something which is linking this activity of the central engine, which is at the center of the star, with the emission region, which is very far away. It has obviously it has to do with the characteristic nature of the jet. But why one jet is like this and another jet is producing softer emission, I don't know.
Thank you.
Okay, if there are no more questions, and so far I spoke about rather all the work or review of some old results in the way we see them today. But now I want to talk about something completely, not completely new, because this original suggestion was made also 20 years ago, but much less known. And this is the idea of gravitational waves coming directly from the jet. The idea is very simple. If you have a jet, you take the jet and you take some material or some energy density, it doesn't matter, and you accelerate it from rest to relativistic velocity. And you accelerate it in a very asymmetric way because it's a jet. So this idea, this fact that you accelerated matter from rest to very high velocity immediately suggests that there will be gravitational wave accompanying, resulting from this acceleration process. So the idea is to estimate this gravitational wave and see what we should do in order to measure them. Because if we will be able to measure them, we will be able to know exactly how the central engines of GRBs and other objects operate. Because this gravitational wave will reveal exactly the acceleration process. So what is the expected signal? So this is the kind of signature that you go from a single jet. If you have many jets, it will be in two jets, it will be superposition of this. And these are jets with different Lorentz factors, gamma equal 10, 100, and different opening angles. And we have here a phenomena which I call anti-beaming. The jet is in this direction, but there is no gravitational wave directly of this kind in the direction of the jet. So there is a sort of an empty cone from which there is no radiation, and there is radiation from the rest, viewed over large viewing angle. And so this is the expected antenna pattern that we could see around the star. What is around the jet? What is the nature of this jet of signal? The signal is not like regular gravitational wave, which goes up and down, but it is more like a heaviside function. It's a signal that goes up and stays constant. This is called, in the professional language of gravitational wave, a memory type signal. So we expect something that goes up and saturate. Sometimes it goes up and down and then saturates, but basically it's the same concept. So this is the kind of signal that we have to expect, with frequency range of about 0.1 to 10 hertz, maybe slightly lower here. And maybe this was too optimistic, maybe 0.01 to 10 hertz. And the canonical objects are, of course, GRB jets. And the magnitude of this gravitational wave is the usual, even so this is not really the quadruple formula. The magnitude is related to the quadruple formula with G times E divided by C to the 4D. This is the amplitude of this gravitational wave. Probably it will be too difficult to detect them from GRBs, because GRBs are far. This will give a magnitude of 10 to the minus 26 for GRBs. But if we have a comparable jet inside supernova, then supernovas are much nearer. The average supernova is much nearer than a GRB, and we may have a source at about 20 megaparsec from us. So this may be a more reasonable source with a magnitude of about 10 to the minus 24. And then a very speculative idea is that sometimes we have a giant SGR flare with 10 to the 47 ergs, but this is galactic. So it's less energy, but it is galactic. And if this is beamed, when we don't know how much beamed it is, if it is beamed, then we may be able to detect it. And this may have even be in the frequency range of LIGO. So detectability is something like this. This is the amplitude. This is the kind of signal that we expect as function of frequency. This is what we would have seen for GW17 or 817, where we know fairly well that the energy was about 10 to the 49.5 ergs, and the distance was 40 megaparsec. This would have been marginally be detected by BBO and by DECIGO. DECIGO is a space mission designed to be in this decihertz frequency. A supernova with 10 to the 51 ergs at 20 megaparsec would have been easily detected by these two detectors, but not by LIGO or even by the Einstein telescope. This is too weak. On the other hand, the galactic magnetar flare, if it is beamed, and again, if it is beamed, will go all the way to the range of Einstein telescope. It will be probably below LIGO sensitivity, but within Einstein telescope. So these things may be detected. And just to mention something which I'm partially involved and very excited, is that there are several ideas to put a lunar seismic gravitational antenna, so to put a gravitational detector on the moon. The moon is very quiet, and because it is very quiet, it is good to detect gravitational wave at this low frequency range. So there are some ideas to build several different competing ideas to build gravitational wave detectors on the moon, and LSGA is one of them. And there is going to be a conference in the workshop actually in the fall in Bern about these detectors. And this is just the right object to be observed in these low frequency detectors. Okay, I sort of I'm not sure what new topic I should start now. Yeah, let me make one more remark that actually should have been done earlier about shock breakout. And then we go back to GRB 170817, the one that accompanied the kilonova and the gravitational wave. This event was very different from all short GRBs. It was much weaker in energy and much softer. So we call them short hard burst, but this was not hard, it was soft. And this is the usual location of these events of short GRBs, and this is here. So people said at the beginning, okay, we looked from the side, and this was just a different Lorentz boost. But this does not work because if we extrapolate the different Lorentz boost, it will go to here, which will not bring it to the other short GRBs. So this was not a regular GRB viewed from a different Lorentz boost. This is very important. What could it be? The idea is that the GRB jet was in this direction at about 18 degrees from us. And we know this now using VLBI observations of the afterglow. And what we saw is this region from which there was no regular GRB activity, but this was a Cocoon breakout. This was the Cocoon that formed, and we saw the Cocoon breakout. This is much more complicated because this, as Zudi mentioned in one of the replies, a shock breakout, a Cocoon breakout from a moving matter is more complicated than Cocoon breakout from a stationary atmosphere, but there is some relationship. And this atmosphere here is not the stellar atmosphere, it is the ejecta, the matter which was ejected in the process of the neutron star merger. So this was a Cocoon breaking out of this ejecta, and again, this signature, which was very soft, could be explained by a Cocoon breakout. Okay, I had one more topic about the TeV emission, but I don't think I have time to go over it. So I just want to mention that in our understanding, 19.114c, which was a very clear TeV emission, it all came from the afterglow, 60 seconds after the burst. And if we take a single zone model here and we model this afterglow and we add inverse Compton to the process, this is just synchrotron, but if we add inverse Compton, we get this inverse Compton, synchrotron self-Compton peak, a second peak. Now, here you have to be careful because you have to take care of the Klein-Nishina effect, and this was done by Nakar and Ando and Sari in 2009, in which they take into account the fact that the cross-section drops when the frequency becomes too high. And then we get this suppression, and this addition of inverse Compton adds a whole list of complications, synchrotron and inverse Compton in Klein-Ishina. So for example, this is the kind of spectrum that you get because of additional of new break frequencies. This is an analytic estimate, and we had a whole effort here to compare the analytic estimate to the numerical estimate, and this will be a new coming paper by Shotaro Yamazaki, Evgeny Derishev, and myself, which will show, for example, what happens. You see here analytic spectrum and two numerical spectrum, and you can see the comparison between the two spectrum, and this will be a very good tool which will enable people to use the analytic result and understand them. So I think that my time is out, so I will stop here. I will just mention that one last thing, that we got very nice fit for the parameters of 190114C. You see this very nice fit for the early signal and for the late signal. And this is 90 seconds, this is 145 seconds. You see, this is the synchrotron peak, this is the synchrotron self-Compton, the inverse Compton peak. And again, this is at late time, the two peaks, and the dip between them in the Fermi range. So this is our model. It has some interesting implications to afterglow modeling, but I don't have time to discuss them now. So thank you and for the invitation to talk, and I can take some questions in the time that remains.
Okay, thank you. Thank you. The last talker from the professor. Any questions?
Well, there are so many questions and so many things you have treated, trying to explain so many aspects. And I think what is our aim is to be specific on some of these aspects which to us are quite relevant. And maybe we will present something in the next days. But let me go back to this TEV radiation. I presume that your model used the blast wave model with very high gamma.
Yes, this is the model that we have here. This is a blast wave. And and we actually estimate the Lorentz factor, and we found that the Lorentz factor is about 150 to get this emission. Yes.
Yes. Okay. One of the beauty now of these observations is that we can have many sources very different presenting TEV radiation. And especially we are focusing of 1908-29A, and some result will be, I hope, if he's recovering in time, tomorrow or the day after by Wangyu. But I just want to point out this. The novelty of the TEV radiation, which can occur on three different ways, very different. In 1807-20b, where you have the S radiation on very late time, on 1908-29, where again you have TEV radiation in earlier phase, and then in 1901-14C, which you have in the very initial one. And the beauty is that we have to understand all these different phenomena and point out what is the physics. Therefore, maybe we will concentrate on one of them, namely 1908-29A tomorrow, I hope, if one view is okay.
Yeah, this was a very interesting burst, 1901, 14C, and these are, as I said, this is our best fit, and this is the this is the best fit. These are the parameters: the bulk Lorentz factor, the Lorentz factor of the accelerated electrons, and so on. There are some surprises here, but I don't have time to discuss them. And interestingly, we can do the fit both analytically, and this is full numerical simulations. But if we do the fit analytically, we can also get reasonable results just with analytic fit.
Well, anyway, we will intervene on this. The other point about the gravitational waves from you mentioned about jet. And let me tell you again, I don't know if we will have time, but in the binary-driven hypernova model, we have, of course, the system is much more complicated than the collapser because it has a CO core, which goes supernova, which creates a new neutron star, and together with the CO core, you have a companion neutron star binary. And what is extremely interesting is that within that model, we can have a very definite possibility in the very early phase of a BDHN tree to emission of gravitational wave.
Mm-hmm.
And that's a signature. It's based on an old idea which I presented paradoxically in the first paper I published in Princeton when I arrived. That paper was about transition between Jacobi ellipsoid and Maclaurin ellipsoid. When I presented that paper, was because at Princeton they were working on the second time derivative of the pulsar period. And we wanted to make some prediction on that. And we did this analysis, and we present to Wheeler. Wheeler said, well, he checked with the person who was working on the second time derivative, which was on the pulsar, and Wheeler asked, should we send for publication? And he said, of course, yes, it's very important. Actually, the referee was Chandrasekhar, because he was the director of the editor of APJ. And instead of criticizing, he was very, very interested. He said, we accept, but you should mention also one of my recent work, Chandra said, which we're, of course, very happy to mention. And this is an old paper, but what we found very interesting is that this could lead to a very clear signal of gravitational wave emission in the very early phase of the new neutron star. The new neutron star rise. The new neutron star is the pulsar which comes out from the supernova. And this, of course, is very, very different from any other mechanism with a very different signature. If we will have the possibility of somebody will talk about that. And that is very, very promising. Of course, it will need far more sensitive detector of LIGO Virgo, but very likely, well, if it could be improved, maybe it will give a signal, but certainly also LISA could be a good candidate. Therefore, we team with your interest, though very different mechanism, to an early phase, not of a jet, but of a spinning new neutron star. And that is extremely interesting. Well, everything else we will have the time to discuss, but we will present some specific case of analyzing within the bidirectional model the acceleration mechanism, which will be different from jets, and especially extremely interesting for what is going on in the case of Cocoon, which we have heard the presentation of Ehud NAKAR, and we will try to add some more important point on this. And Tsvi, let me thank you, and let's keep our mind open. And let's hope that people will recover in time in these hours.
Okay, nice talking with you, and bye to you all.
We will try to make a presentation, to schedule this, a new schedule in the next hours, and we are also thinking to have between in the evening at between 5 and 6 o'clock tomorrow, a discussion with Petrosian and Dainotti and other people to discuss some of the points that we will present in the morning. Therefore, if you cannot be in the morning, try to be at least in this general discussion in the between 5 and 6 o'clock. But I try to convince you to be present in the key discussion in the morning, if you can connect.
I'll try. I'll see if I can make it.
Especially Nakar.
Okay.
Thank you.
Thank you. Bye.
Thank you. We have break or not?
Yes. Hello? Can we return?
Okay. Good morning.
Good morning. Okay. Mariateresa CROSTA, sei pronta?
Sì, I will share my screen.
Yes.
Could you see my screen?
Yes, yes.
Okay, perfect. Okay, thank you for your invitation. Today, I will present how Milky Way can serve as Einstein paradigm thanks to the Gaia mission. My talk is essentially based on two ingredients. One is relativistic astrometry, which implies to develop and implement theoretical, analytical, numerical models completely based on general relativity, and which include also relativistic attitude for increasing accurate astronomical data, and started with Gaia. And then gravitational astrometry that is used for data interpretation to study the impact of general relativity models for fundamental physics and local cosmology. especially for relativistic test that goes from the solar system to the Milky Way scales. And also, thanks to combination of two ingredients, we are able to introduce a novel way to detect gravitational waves. As probably you will know, because my colleagues last week gave already a talk about Gaia. Gaia is measuring position, direction and distance and velocity over 1 billion stars in our galaxy with an accuracy of 1 mark/second. The final goal is to produce science with 1 or 2 billion objects in 3 dimensions, from which able to enable us to understand the structural evolution of the Milky Way and also to plan some relativistic tests. Basically, in this focal plane, Gaia is combining 3 fundamental measurements in astronomy: astrometry, photometry, and spectrometry. So the Gaia census is detailed star by star, along with the knowledge of the intrinsic properties of the stars, such as temperature, brightness, age, and composition. Just to give you an idea, 1 microsecond could be compared to the size of the star on the tip of the Mole as seen by Jupiter. And Gaia is continually scanning the satellites, so it's measuring angles as in the past times. And here you see to sketch about the scanning works, the scanning law of Gaia. So to assure scale coverage, Gaia is combining along with the orbital motion around the Sun, also a spin motion and the precession angle with respect to the Sun direction. In such way, after during the mission is able, of course, to map the entire galaxy. And Gaia is measuring, I have to say, absolute parallels, because it's working on space and on Earth. To measure small angles means, in practice, longer distances. The location of an object in astrometry is considered reliable if its relative error is less than 10%. This means, for example, that if we take example Parcos, the previous space astrometric mission, which Parcos had an accuracy of 1 millisecond. That means that with 10% accuracy, with the Parcos, we reached just the scale of 100 parsec. With Gaia, since we are measuring 10 microseconds, for example, for bright stars, we're able to reach the galactic scale. And for this reason, the final goal of Gaia is just to measure to understand the evolution, the formation, the structure of the Milky Way. Quite recently, Gaia has delivered its third release. These are the number of this release. You see that Gaia has observed already almost 2 billion stars, and is able now to well characterize many of them, especially to the astrometric 1/5 billion astrometric parameters. There are a subset that also 33 million as also radial velocity. So we are gaining information of how deep is our galaxy, and also for other objects. This was the first picture of the Gaia, the total density map of star produced by Gaia with DR1 after 14 months of Gaia's routine operational phase. And you can see all the artifact here of the scanning law of Gaia. And now this is the last one, the total density map, that is completely changed. You see still some artifacts, but it's really improved, and we see after 34 months also we have details of the satellite galaxy of the Milky Way. My colleague last week, I suppose that they already discussed also these new maps produced by Gaia. So this is just to inform you of how much is detailed is the science with Gaia. So we have map for the radial velocity and stellar motion, intergalactic dust, and even chemical composition, tell you about the history of galaxy. Besides the main goal, which is the Milky Way, according to different parallaxes accuracy, the scientific output of Gaia span from the solar system to the Milky Way scales. Means that in the solar system we're able to test parameterize post-Newtonian parameter. We are able to perform local gravitational tests related to the body of the solar system. By 200 passes, Gaia will be able to detect 10,000 exoplanets, and so on. So Gaia is going to to define the calibration for the distance scale, the calibrators for the distance scale, and also to give a calibrated accurate detail about each diagram. But any of these scientific problems cannot be possible if behind the scene there will be there is generativistic astrometric modeling for the analysis and data processing. In this picture, in this video, you can see that how the solar system body affects the measurement of Gaia. We see the scale of the microsecond, and the sun in this video has been removed. And you see that the main at L2 point where Gaia is operating are present the ever changing overlapping gravitational field due to the solar system body. And then at the 1 microsecond threshold, you can see here that the sun is ever present, as you told before, so we cannot avoid the presence of the sun, and also Jupiter, and also the other planet. Even the oblateness of the planets such as Jupiter and Saturn give contribution to the light deflection. And for this reason, we need to develop a full relativistic analysis of the light trajectory from the observer to the stars. Of course, the metric that we use for data analysis and processing of Gaia is that one given by the Yau resolution, which implies the post-Newtonian approximation of the field solution of the Einstein equation for the solar system. And if we would like to have the 1 microsecond accuracy for the geodesics, we have to keep term of the metric, the off-diagonal term of the metric, which include the velocity of the solar system bodies. So high astrometric accuracy necessarily translates into need of using generativity, and in the development of a fully self-consistent astrometric relativistic models according to generativity. And with Gaia, we have a large uncharted experimental domain, because relativist is the first time that we are implementing relativistic astrometry. The final catalog of Gaia of position, proper motion, and parallaxes constitutes the realization of a quasi-inertial kinematic rotating global optical frame that accomplish the AU recommendations, and is the first direct materialization of dense absolute reference frame to visual bands, and itself is one of the most important fundamental physics tasks that Gaia will accomplish. So for this reason, the consortium constituted for the Gaia data reduction agreed to set up two independent global sphere solution, AGIS and GSR. I will let you explain later a little bit. And these two independent global sphere solution has also two independent GRM model, the GRAM model, the Gaia baseline relativistic model, and the Ramond model, relativistic astrometric model. They are both models work in the same Gaia data, so actually, at the moment is in place a validation process between the two models. This will help us to control on the error badge at the level of microsecond, since the solar system generates several perturbations, and which depends also for different observation times and for different satellite positions. This allows us to rule out a possible spurious contribution, to consolidate the result via an independent mutual cross-checking between the model, since the model implemented an independent relativistic model, theoretical model, and independent relativistic attitude model. Cross-checked theoretical model are capital importance to interpret the same data. So any discrepancy between relativistic model means either validation or generativity, or or a clue that we need to refine our relativistic approach to generality. So it's a very fundamental this part that allows Gaia to guarantee its scientific products. So basically, Ramond is a top-down approach, so it's based on GRB protocol measurements, and it has no prior approximation, keep everything quite general, and use approximation only where it are needed. And is a framework relativistic astrometric model with increasing intrinsic accuracy, in order to test bed, to have each model is a test bed for the improved, the next improved model. On the other side, GRAM is essentially based on classical astrometry. So the light direction, the observed direction is converted into a coordinate one via several steps, which divided the effect of the aberration, the gravitational deflection, the parallax, and proper motion. Instead, Ramond taking into account everything when trying to solve the null geodesics. Ramond is implemented in the global sphere reconstruction, GSR, of the astrometric verification unit at Italian data center DPCT. The DPCT is among the 6 data centers across Europe, the only one that is specialized in the treatment validation of astrometric data, and is hosted in Altec in Turin under the scientific supervision of the staff in Afoato for ASI. And it's a big archive of raw data to exploit also for the future after the end of Gaia. Basically, the unknown of Ramond is the light projected on the rest frame of a local barycentric observer. So the observer is at rest with respect to the BCRS, and of course it takes into account all geometrical property of the congruence of curves of this local barycentric observer. So this is the final equation for the Jez equation for Ramond that include can be solved both in the static case or in the dynamical case when we consider the velocity of the solar system body. Each of these equations, of course, is constrained by the observer direction of the satellite. In fact, the astrometric observable for Gaia in the Ramond model is the cosine between the incoming light direction once projected on the rest space of the satellite, and with respect to also the relativistic attitude of the satellite. One observation is constitutes a condition equations. So when we have many of these equations, since Gaia is surviving all the skies, and then we're able to have this a huge amount of data that we can put in this differentiation by this equation, and we can in this case we can put in this differentiation around catalog value. We can model this function f contain our relativistic model, which depends on the astrometric parameters, and also with other unknown. Of course, this equation is constrained not only by astrometric parameter, but also by instrument modeling, the error budget, and so on. So one of these, in this huge amount of equation, a system of equation that we solve in an iterative method, there is also the gamma parameter that, of course, I have not to explain to this audience the importance of the gamma parameter, but since Gaia is observing light deflection all over the skies, Gaia is performing a massive repetition of the Eddington experiment, but with the technology of the 21st century. And given the number of celestial objects, so it's Gaia is performing a real Galilean method applied to the sky, and direction involved, we can say that Gaia is the largest experiment in general relativity ever made since 1999. Now we are at the beginning we are expecting the gamma that deviates from 1 from the value predicted by general relativity at the order 10 to -6, but now we are not so sure about this value, but probably we are waiting for the last release of Gaia, since this, of course, is the measurement gamma is a measurement of global astrometry. So it's better perform, more star we have, better accuracy we have on determination of these parameters. Just briefly, I would like to introduce the fact that with Gaia, we have performed the test to test the light deflection around Jupiter. This was studied before in 2006. So the light deflection Jupiter, as seen from projected on the sky, can be decomposed in one deflection along the radial direction, one deflection north to radial directions. This we studied, and this was possible to study this effect by catching brighter star close to Jupiter. So was decided to a little bit to change the scanning law, the initial phase of scanning law Gaia to catch this bright field in 2017. Basically, by applying a differential astrometry, it consists to take each scan portion of the sky made by Gaia and glue together all these scans through a delicate procedure on the raw data that is sketched here. I don't have time to explain, but if there are any questions, I can explain it better. And so at the end, we were able to measure the total light deflection produced by the planet. This is the first time, I think, it's on the optical band. And as you see here, this deflection included the monopole, the quadrupole contributions. And basically, we have seen of the light deflection change of target stars is approaching the Jupiter mass. And this is the total light deflection projecting the long sky direction of Gaia. And this is the predicted one. So now we are performing a test in order to see if we are able to measure the quadrupole effect. So the lesson from Gaia is that with Gaia, we are in the era of gravitational astrometry. For the Gaia-like observers, the weak gravitational regime turned out to be strong, especially when one has to perform accurate measurements. Gaia is delivering as relativistic kinematics, full consistent with general relativity. And since we have a relativistic approach for the data analysis and processing, we try to export this philosophy, let me say, also to the reconstruction of the Milky Way. In more general sense, any subsequent exploitation of the Gaia data should be consistent with the precept of the theory underlining the astrometric model. And let me say that a generativistic picture of the Milky Way can ensure a strong and coherent local cosmological laboratory against which we can test and model the galaxy. Also any alternative model also to general relativity. For local cosmology, here we mean how well distances and kinematics at the scale of the Milky Way disk compare with the lambda CDM model predictions. Let me say a few words about the weak field regime at Milky Way scale. In general, one assumes that gravitational potential relativistic effect at the Milky Way scales are usually small, then they are negligible, and locally Newton approximation is retained valid at each point. But if we think to some extent to apply a post-Newtonian metric to the galaxy, as we did in the solar system, we see that the off-diagonal term, when we consider the typical velocity of galaxies, is about 120 microseconds. So, and this is well contained. The individual astrometric error is 100 microseconds. So, in certain, which we want to apply the same reasoning that obliged us to use general relativity for data analysis and process of Gaia data, we have to say that the weak relativistic effect could be relevant. So, and we know also that the small curvature limit in general relativity does not might not coincide with the Newtonian regime. So we in order to pursue a relativistic Milky Way, we decide to compare general relativity and classical CDM model. Of course, since Gaia is directly measure the relativistic kinematics of the stellar components, so is able star by star to trace the gravitational potential inside the galaxy, and the rotation curve are a distinctive feature of spiral galaxies, like a kinematical signature for each galaxy. So we decide as a first test to test, of course, the flatness of the Milky Way rotation curve. The classical lambda CDO model basically comprise a bulge, a thin thick disk, and halo. Here we reported the density associated with this component as present in literature, and this component depend on several parameters, from the mass, the scale length, height of the fin of the disk of the component, the halo scale density, and so on. Each of these components contribute to the Poisson equation. So basically, in the classical model for the Milky Way, the dynamic is ruled by the Poisson equations. And from solving the Poisson equations, we get the velocity, Milky Way classical Milky Way velocity profile. On the other hand, it's quite difficult to find the exact solution of Einstein's equation, especially if we think that our galaxy is a multi-structure object. And so we decided to start from a simple assumption. So to take, first of all, to consider a dust model. So a space-time endowed by a stationary axisymmetric metric. We assume reflection symmetry. And so the disk is an equilibrium configuration of pressure-less rotating perfect fluid. And then, of course, we consider this metric is not taking into account the central the bulge of the central region. one solution of this kind of metric was found by Balasin and Grumiller, who at our disposal was the simplest assumption for a galaxy model. Simplest means that, of course, we have there is a dust, and when we solve the Einstein equation for such line elements, from one side, we have the relativistic density. On the other side, from another equation, we can solve the velocity profile, which is quite simple because it depends only on three parameters: the bulge size, the galaxy size, and the velocity in the flat regime. But this model is constrained by this condition that the zeta coordinate should be less than the bulge size. Then, if we consider stars in circular motion according to this galactic metric disk, of course, the stars can be represented or with respect to coordinate or with respect to the local non-rotating observer like ZAMOS. So our ansatz for our first test was to see that to measure the velocity, the rotational velocity of this star with respect to the local rotating observer, which this is the expression, of course, when we compare these two expressions, and the final equation that, of course, you can see there is this difference from the simply classical one with the angular, which is only the angular velocity, because are more terms related to the geometry. So this was our first ansatz, independently of how this is the kind of matrix, this definition of the spatial velocity measured by locally rotating observers. Of course, if we consider a co-rotating dust with respect to ZAMO, it turns out that the spatial velocity is related to this n term that was solved by Balasin and Grumiller, that some way is proportional to the off-diagonal term of the metric. So this is a clue that some gravitational dragging is working at disk scale. So our ansatz was the Milky Way rotation curve is driven by dark matter or geometry. So this was the question that we tried to answer with the DR2 data of Gaia. So we selected the best sample at the type of with DR2 first. Now we are doing the same selection with the TR3 Gaia. So this is a sample of star that came only from Gaia data in order to have a very homogeneous samples. And our selection is constrained by this strict requirement that so the parallels has to be good to 20%. It should be a complete Gaia asymmetric data set. So we have also radial velocity with 20% uncertainties in such a way we were able to put in place a proper 6-dimensional reconstruction, the phase space location occupied by each individual stars as derived by the same observer. I stress on this point because it's really the benefit that we have from Gaia. Of course, for DR2, we had to cross-match with the other catalog in order to characterize the sample. Now with the DR3, we don't need this because we have also the information about the sample. So this selection is aimed to have the best angular momentum sustained stellar populations of the Milky Way. With DR2, we had a sample 5,277 early type stars and some 300 the most classical type 1 Cepheids. With DR3, now we have a very homogeneous sample of 1 million stars, including GRB, O, A, and disk Cepheids. With the DR2, since the parameter space is too large and simple nonlinear fit is not suitable, we decided to use a Monte Carlo Markov chain method to fit the Gaia DR2 data. And in this diagram, you can see the differences. That the red line is the velocity profile fitted by the Gaia data, and the blue line the classical model. And you can see that for high likelihood analysis, the two models appear almost identically. And statistically, they are perfectly equivalent. But I stress that the relativistic model, we had one more parameter. I will tell you the next slide. Has only 4 parameter, while the classical model here has 7-9 parameter. Then also the bulge with this model is able to give a dimension from the velocity data of the bulge, which is quite similar to the classical one. Then if we compare the density we take the other Einstein equation related to the density, and differently from Balazine and Grumiller, we had this new parameter that is related to the conformal factor of this asymmetry stationary metric. So, and we compare at the sun, the density, of course, we had only 1 point at the sun with the light. So for this reason, the density enter in the likelihood function only at the sun. So we get the same baryonic mass density as obtained by other work in literature. So this perfect. So from one side, we fit the flatness of Milky Way curve with the relativistic velocity profile. We don't need the extra mass. And one more text we performed that in order to see if really the gravitational dragging is working or not. Since the Balazine-Grumiller velocity profile does not discriminate with the baryonic gravitational contribution, we in some way we had to build this, calculate the Milky Way classic baryonic contribution with the effective Newtonian profile, which is defined in classical tests about galaxy by Bin and Tremaine. And so in order to calculate, so we put the density calculated by the relativistic model inside this equation profile, the Bin and Tremaine, in order to get an effective Newtonian velocity due to the relativistic counterpart. Then we subtracted in some way the equivalent from the classical model, and then of course, since the BG model is valid very close to the equatorial plane, we need to also implement a minimization procedure in order to find the effective vertical distance where we can perform this comparison. So by subtracting at this point this effective Newtonian velocity in BG, that is due only by the baryonic component to the total relativistic velocity, we are able to compute the amount of rotational velocity across the Milky Way plane to the gravitational dragging. And as you can see over the radius explored by the Gaia data, here the halo contribution is compensated by the gravitational dragging. So this is favorably points to the fact that the gravitational drag-like effect will sustain a flat rotation curve. This was our answers that we tried to prove. Now, next improvement is, as I said before, to use DR3 data. So if we use the Gaia DR3 plus mass photometry, and we put a cut, this cut, of course, we are in good position to do this because the spatial distribution of our sample is really close to the disk of the galaxy. But and you can see this is this point favorably to the relativistic model. But there was a bias in this diagram that was, we use a Tombrot diagram that kept stars only around 250 to 40 kilometers per second. So we we forgot about the previous plot, and we produce another one with only DR3. This plot takes into account 500,000 objects, as I said before, including RGB, O, and SFAs. Then you see again the different component of the classical Milky Way, the gray part, and so that sum up for to form the blue curve, and the red one is the relativistic one. But this is it's a plot of all the stars that we perform again a Markov chain, Monte Carlo Markov chain method, but we use here equal error to each for each stars. Equal means that since we are working with the exquisite Gaia data, so in order not to introduce bias by bootstrapping or other, I forgot to say that each this point is a median of the bin that we group the star in bin. And of course, there is also another bias here, because with Gaia data, we are able to go very close. I have to say not too close, but close to the bulge. You can see from the Milky classical part, the bulge is minimized. The role of the bulge is not so prominent. But this could be wrong, because below 4 parsec there is the bar, so it's not really asymmetric, the disk. So we decide to cut this, and now this is the curve that we produce with the DR3. I'm showing you for the first time the work is a submission. Of course, we tested this curve. We are testing the sample with the different candidates. These results are fitting. Since we would like to be sure that the results are independent from any method that we use to fit the data. So we are testing with the different stellar sample to understand which is the best way to fit the data in order to be sure they are results. This is we impose these ansatz because we want to, in some way, we choose the most simple cases, let me say, in order to follow the Occam razors. So apparently our result says that dark matter, as far as Milky Way is concerned, is driven by geometry. And so we are not saying not anymore that general relativity is still the standard theory of gravity. And this is very important, that once we have defined this geometry for the Milky Way, this same geometry, I mean, the physics can be exploited for also other galaxies, external galaxies. Of course, we need to improve the theoretical models, in the sense that it's quite, since the result is very nice, because our result says that they are similar to the classical model that are currently used to infer the dark halo matter and so on, the contribution of dark halo matter. But of course, we need to, for example, to extend it to numerical simulation, to more complex simulation, to compare with the Gaia data that are much more complex. I forgot to say that we also made a cut in eccentricity. We chosen the million sample star, are stars that have low eccentricity, and so on. So in order to fit the real data of Gaia that are much more complex, we need also a more complex model, numerical relativity. Maybe we have to implement Einstein blazon system solvers, and so on. Now, the last part I want to talk that relativistic astrometry, of course, help us also to introduce a new detection method of gravitational waves. Gaia is simply recovering the local line of sign from within the gravitational field of the solar system, but of course then is matched with the gravitational field at the star. But of course, in the between can intervene some gravitational waves, the perturbation of the space-time. So it means that we have to add some in the solar system. Gaia can detect, or Gaia-like satellite can detect also gravitational waves in the matrix. This means that, for example, at least the order has been evaluated for astrometry. The lowest order of gravitational waves is the level of 1 nanosecond. By exploiting the definition of the cosine, but in a differential way means that by considering 2 lines of sight instead of 1 line of sight with respect to the altitude, which will be impossible because a nanosecond, if you want to consider an observable related to the attitude of Gaia, it's impossible to detect gravitational waves. But instead, if we consider 2 lines of sight and we use the same relativistic model that we used for Gaia, we are able to obtain a new gravitational wave observable, which depend on the unperturbed star direction, I mean the Minkowskian flat direction. It depends also on an extra shift to the passing gravitational wave on the line geodesic. It depends on the gravitational wave strain and moreover from the telescope optical resolution. I mean from the angle between the two unperturbed directions. This new observable practically is going to aims to monitor small variation of the basic angle between 2 directions. This small variation due to passing gravitational waves. Then if we implement if we see a close far direction and we implement this new observable along 3 direction, for example, in a 3 telescope, and telescope with the 3 ways, we are able, this new observable is able to determine with the sub-arc second accuracy the direction of gravitational waves, because of course along one, if for example gravitational waves propagating along zeta, the astrometric signal will be completely 0 along the propagation direction of gravitational waves, since it depends on the strain, and simultaneously in the other direction will be maximus, and we can measure the gravitational wave. Here there is some, for example, for a supernova with a frequency to 10 to the cube frequency of the 1000 hertz. And then this, we can have a signal around the microsecond. And we can improve, of course, we in an order of magnitude, of course, if we play with the optical resolution. This value have been, for example, this is the first row, the value is 10 mass, is the optical resolution HT. Of course, if we improve 1 order of accuracy, we have a very strong signal about 41 microsecond. So the advantage of this equation is not only to give us the direction of gravitational waves, but also possibly to amplify the signal if we choose a good, an optimal optical resolution. This is just a simulation of such a signal for binary star inside our galaxy. And as you've seen from these graphs, the signal is above 1 microsecond for large cases, however, for many frequencies ranges and many distance, many parsecs, range of many distance. So this is very promising. And of course, if we complicate the scenario, considering also different orientation of the incoming gravitational wave with respect to the reference frame defined at the detector, of course, the direction of the gravitational wave will be that one that's also small with respect to the other directions. This gravitational wave antenna, of course, the first simulation tell us that this detection can cover signal with the frequency goes between 10 to minus 10 to 10 to minus 4 or to 10 to minus 10 to minus 1 to 10 hertz, from DCR to 10 hertz. So it's quite complementary to other efforts in detecting gravitational waves, and of course it can be used, this kind of detection as a gravitational wave sentinel. So with which we can build statistic on event rate by surveying all the GB sources. And if we if you look to the amplitude pattern function, we see that and compare the detection volume of such an antenna, astrometric antenna, with respect to the interferometer efforts. We see that the astrometric antenna cover larger volume and also many directions, and also cover directions that are blind for interferometer. So I'm going to finish here because I think that I ran out of my time. So I hope that I've convinced you that the mandatory use of generativity has opened a new possibility in strategies to apply Einstein theory in classical astronomy. Let me say that before Gaia, this was not possible. Any generativistic test performed by using Gaia, both at the solar system or Milky Way scale, play a reference role for other tests, much like the Sun for the stars, the Earth, Jupiter for exoplanets, our galaxy for other galaxy, non-spherical weak lensing, and so on in the case of quadruple for Jupiter. The first results are very promising. With Gaia, we have a full 4D relativistic sky, let me say, because also there is also the time component that I don't mention you, but it's inside the geodesic equation. We have tested the Milky Way rotation curve. We have introduced a new way to detect gravitational waves. So, and this push towards more complicated solution for the local cosmological test and so on. Thank you very much for your attention. I finished. If there are questions. Sorry if I've been rushed.
Okay, thanks to the last talk. Any questions for the speaker?
Well, very, very impressive, extremely impressive. And of course, I mentioned already in the previous week that the first person to be interested about the general relativity process inside our own galaxy was Enrico Fermi, who proposed this topic to Maury Gell-Mann as a PhD thesis. Maury signed the wall in Villaratti, and at that time he told me that, of course, he changed his mind at the time because the data were not so clear and the goal were not so clear as instead the field of particle physics, which urged to the introduction of quarks and which they became very famous, got the Nobel Prize. But let me go to more, to different aspects. I understand what you are doing, and it's very, very, very remarkable. But at the same time, I am working in this house with our group. And I don't know if we have time to show you some of the results. Maybe Carlos will present some. There is a fight going on about the galactic center. We have an idea that dark matter and not a black hole be at the galactic center, as you know. And this dialogue is keeping going. But something extremely different happened in the last few weeks. I mean, they are the data on the S stars moving around the galactic center very regularly. And we are working on this to see what limit we can put on dark matter. But in the last week, something incredible happened, a different technology in the optic, in the was developed. And there are 6 papers just published which give evidence for an existence of a Kerr black hole in the galactic center. Of course, this is no matter for you at the moment, but you have to keep in mind that this reality is going on. Mm-hmm. And I think that this, I have very strong doubt about the validity of this approach. And maybe we should comment why I think it is absolutely not possible to have a black hole, because one of the topics which some of you are going to discuss is the presence of a black hole with E over m very large in the galactic center. I think this can be absolutely, certainly excluded. Therefore, I just want to mention, Mariateresa, that yes, the dialogue is complicated. It's complicated also because there are statements very different, using very different technology. But when the different technology lead to inconsistent conceptual data, this is very worrying. Mm-hmm. Especially all the other work that they are trying to do, M87 and so forth. We are still working on this, but just to let you know that it's good to keep an eye open. Certainly to understand if baryons are enough, but even the galactic center one is a topic of very hot confrontation during this house. Just a comment.
Yes, Gaia data are able to do this, so we can test any model with Gaia data. So there are prediction, of course, we are not suitable for the galactic center, but we can match this test with the other galactic test that goes towards the galactic center.
Yes.
So this is, we moved from the first simple assumption, and now, since we had good result, it's worth going further to test, why not any other model, a theoretical model, in order to see which is the best. Of course, data are independent from theoretical model. Yes. And one should be very careful when to fit the data. And so, especially when we have a wealth of information, as in case of Gaia, so to keep, to try to understand which is the best fitting method in order to have independent results. And this is the possibility that we offer. But would be not possible if Gaia has not be in the core of Gaia contains general relativity. This would be possible in any way. So, and what I see because from the side of the astronomer, they use classical, they use Newton regime. Could be enough, but we have to check to what extent this is enough or not.
Absolutely, I could not agree more.
Yes, and this is what our answers try to put general relativity in the context of astronomy, starting from the Milky Way, of course.
Yes, but let's be ready to discuss also the galactic nuclei.
Okay.
Okay, very, very
Thank
nice.
you.
Congratulations.
Thank you very much for your invitation.
Okay, any more questions? Or let's thank the speaker again. Let's move with the next speak.
Thank you very much.
Thank you.
Who is the next speaker?
Okay, it should be me. Can you hear me?
Yes, yes.
Okay, thank you. I will share the screen.
Can you share your screen?
Sorry?
Can you share your, okay. Yes.
Yes.
Yes, you can see your screen. Okay, the next speak is the Petr KOTLAŞÍK. We'll talk about statistical discuss around the center black hole as possible relativistic model of the galaxy. Okay, go ahead, please.
Okay, thank you. Thank you for the opportunity to speak here. So my name is Petr KOTLAŞÍK. I am a PhD student at the Charles University in Prague. And as you can see, I will speak about a particular solution to Einstein equations describing slowly rotating thin disks around the black hole. And also if it's possible to use it as a relativistic model of our galaxy. And more importantly, if the dragging effects present in the solution can somehow contribute significantly to the rotational curves without introducing the dark matter. And I will start directly with the latter question. So if this model can explain, at least partially, flat rotational curves. And unfortunately, the answer is probably not. So I could end here, but I think it will be useful to explain you why I think so. So my goals of this presentation are, first, I would like to speak about why we should look for different general relativistic model for a galaxy than the Balazs and Grumiller, because as I will show you, Balazs and Grumiller has, I think, quite severe non-physical issues, which should not be, which should be taken account. Then I present you the advertised disk solution around the black hole, and in the end I will show you some numerical results, how the dragging influences the rotational curves. And even though this solution cannot explain the flat rotational curves, it can be used elsewhere, for example, in active galactic nuclei, where also is supposed to be black hole and some disk around. Okay, so let me first speak about the proper spacetimes suitable for this kind of job. We call them circular spacetimes, and they are assumed to be asymptotically flat and without the cosmological constant. They should be also stationary and axially symmetric. That means that there exist two Killing vector fields. One is space-like and the other time-like, and there is an axis of the symmetry, which is locally flat, and the space-like Killing vector field should be zero there. And circular spacetimes are also orthogonal transitive. That means that the planes perpendicular to the Killing vector fields are integrals of manifolds. And we can use these symmetries to introduce adapted coordinates. So we introduce the time t and the azimuthal angle phi as the parameters of the Killing symmetries exactly in this way. And the remaining two coordinates can be chosen in such way that the respective part of the metric is diagonal. And the standard usage are the wild coordinates. So let's say generalized cylindrical coordinates or isotropic coordinates, generalized spherical coordinates tied with this simple transformation. Then the resulting metric is independent of time and the azimuthal coordinate, and the orthogonal transitivity means that all sources follow the Killing vector fields. Therefore, they are performing something what we can call a circular motion. And before I show you the most general metric of this kind of the circular spacetime, let's talk a bit about Balazs and Grumiller solution, which Mariateresa talked about before me. And this solution is, as you saw, is possible. This solution explained flat rotational curves without introducing dark matter. So the Balazs and Grumiller obtained a solution that should describe a rigidly rotating dust. And under the assumption that the dust is following the integral curves of the time Killing vectors, then the metric can be calculated in this way. And Balazs and Grumiller provided a solution for this metric function n, which you have seen before. And this another metric function psi is given by these Einstein equations. This sigma denotes the dust density, and this v is the velocity of the dust measured by a zero angular momentum observer. And from the fit done by Dr. CROSTA and her collaborators, the parameters of our galaxy are around these values. Now, I believe that, unfortunately, the full physical interpretation of this solution is not very clear because there are severe problems at the axis and which should be addressed and cannot be ruled out, really. So Balazs and Grumiller already noticed that there are somewhere fast superluminal velocities of the dust when you are too high on the axis. But there are also additional sources. There are singular rods between on rho equals to 0 between these two parameters of z, where the density is diverging and also the Kretschmann scalar is diverging there. So there is really a curvature singularity. So we have two singular rods on the axis. Then also the norm of the space-like Killing vector is not 0, it's even negative there when z is greater than r0. That means that this Killing vector field is time-like there, and because it's not 0, the part of axis is not really an axis. It cannot be interpreted as the axis because the norm of Killing vector is not 0 there. And also, if you integrate really the second metric function psi and demand that it goes to 0 in the radial infinity, which it should, because we are assuming the asymptotic flatness, then you get non-zero value, some constant on the axis. And from Einstein equations, it means that this non-zero constant is everywhere on this part of this axis. But this validates the local flatness condition. So there is a conical singularity present in the middle of what is supposed to be the galaxy, which connecting these two singular rods. And from Reichenberg equation, if you have shear-free and excitation-free case, which is that rigidly rotating dust, so you find out that the vorticity of the dust geodesics is proportional to the dust density, and it is infinite at the singular rods. Therefore, to stir up the discussion, I can propose another interpretation of the Balazs and Grumiller solution, and that it describes non-rotating with respect to the distant stars, no rotating dust. And there are two additional sources on the axis, which is rotating extremely fast, bringing some dragging effects into the space-time. And these generating dragging effects fix the dust particles at their positions. And this is a kind of preliminary interpretation. We still need a better understanding on these sources at the axis. And I think it is not really clear if you can cut out the nice areas, the part that really fits the rotation curves of galaxy, that means in the equatorial plane and far from the axis, and smoothly match it to some reasonable, more reasonable exterior solution. So I think we should really look for a better relativistic model of galaxy than the Balazs and Grumiller. And one possibility was to use a gravitational field generated by a slowly rotating disk around the center of black hole. So I will, so let's back to the beginning and to show you how the solution of this rotating disk looks like. So this here, you can see the most general metric satisfying the satisfying all symmetries I talked about. So it is an axially symmetric and stationary metric. And in while or isotropic coordinates, it can be written in this way, with four unknown metric functions, b, nu, zeta, and omega, which are dependent only rho and z. Then we have to plug the metric into the Einstein equation and try to solve it, of course. So first, we take a look on this b and on this zeta. So if this condition for the energy stress tensor is valid, which is valid, for example, for the dust or ideal fluid, then the Einstein equation for B is just this simple one. And there are two standard choices, either the simplest solution of this equation, E equals to 1, or still simple but longer expression for the capital B, this one. In fact, the choice of B just really means a redefinition of y coordinates. So if I have the coordinates, the y coordinates with the steel dust, those with the capital B equals to 1, then by this transformation, I transform to the metric where B is non-1. And let's say geometrically speaking, that means that for a Schwarzschild black hole, which is also the solution part of this class of spacetimes, the choice B equals to 1 renders the black hole as a singular rod. Meanwhile, the second case, if we choose the K, the constant K to be M, the mass of the black hole, then the black hole is really rendered as a spherical, the horizon is spherical in these coordinates. Great, the other metric function zeta can be obtained by this simple integration, where the derivative of zeta depends through the Einstein equations only on nu and omega. And nu and omega has clear physical interpretation. Nu is the Newtonian analog of gravitational potential. Meanwhile, the omega function corresponds to a dragging angular velocity. And Einstein equations for these two metric functions looks like here. Great. Now we have to talk a bit about what is on the right side of Einstein equations. And we are looking for a solution of a thin disk. Therefore, we assume that the disk is uncharged and lying only in the equatorial plane, and it is infinitesimally thin. So there is everywhere the vacuum, only the distributional source in the equatorial plane. And we also suppose that the disk has not radial pressure. Then only 3 components of the stress energy tensor are not zero and proportional to the delta distribution. And in order to stay within the circular spacetimes, we have to demand that all sources of the disk follow the killing vectors, therefore performing the circular orbits with some angular velocity. And this corresponds to the 4 velocity written in coordinates in this way. And any such disk, any such thin disk without radial pressure can be interpreted in 2 ways. Either it is a single component ideal fluid with a certain surface density and certain azimuthal pressure, which keeps the orbits on their position, or it is 2 counter-rotating dust streams following single circular geodesics. Great, so, and as you could have seen, the Einstein equations are quite complicated. So we have to make our lives a bit easier so we can try to solve them using some perturbation scheme. And our perturbation scheme will be very simple. We take the metric, choose B this way, so the horizon is really the spheric horizon, then express all the metric functions and also the sources as a power series, write down the required Einstein equations and try to solve them. Technically speaking, this means this, just rewriting the metric components in the power series. And as a background, we choose the solution of the Schwarzschild black hole, which is written in isotropic coordinates in this way. And this is the black hole of the mass, capital M. Substituting this into the Einstein equations and subtracting the Schwarzschild terms, you arrive with these coupled differential equations for every perturbation order. And surprisingly, you can find the green functions for this coupled system. It was done by Will already in the 70s in terms of multiple expansion. So there was a somehow double expansion involved. First, the expansion of the metric itself, and then the expansion of each perturbation order. Then Dr. Křížek and Professor Semerak managed to express the green function in closed form, which was suitable to integrate over some extended source. So to really integrate a solution describing a rotating disk. So let's first take a look on the potential. So if you take a look on the equation for the potential, then you may notice that the dragging comes in higher orders, higher than second orders. Therefore, if we assume that the rotation is slow, then we can rule out these big term. And if we choose B equals to 1, then what rests is just the Laplace equation in cylindrical coordinates, which is the same equation in Newtonian's gravity and also in a pure static case in general relativity. So if we assume the slow rotation for potential, we can use any solution to Laplace equation. And then reparameterize the coordinates to those of our capital B. And we found some suitable closed form solutions quite recently. And I will give you a brief how we derive with the solution. So it consists on expressing the green function of the Laplace equation in this form, where these j's are Bessel's functions of the zero order, and then the potential of the thin source of some surface density is given by this double integration. So we have to in order to find the solution, we have to perform this double integration. And our strategy was first to consider some elementary density terms, some simple ones, and then to use the linearity of the Laplace equation, and by a suitable superposition of these elementary density terms, construct physically reasonable disk with parallel density profiles. So the elementary density terms we are considering are in this way. So it is just an even power in the radial coordinates. And this kind of elementary disk starts at 0 and goes to some finite radius b. And if you perform the integration, you can ask, for example, Mathematica, and Mathematica will tell you that this is in fact just this generalized geometric functions with some arguments. Curiously, this hypergeometric function can be expressed as a finite sum of some Bessel functions. And here are just some relations you can use for this to really obtain this expression. Hence, the solution for potential is reduced to find this kind of integrals. And this is really just a Laplace, kind of Laplace transformation of Bessel's function products. And this integral has been studied before, for example, by Conway. And in fact, you can obtain closed form formulas for some lower indices here, and then use various recurrence relation to obtain closed form formulas for any of the integral of this type. And if you do that and plug everything in, you arrive with the gravitational potential due to this elementary density term as this expression, where h is Heaviside step function, e, k, and pi are all three complete elliptic integrals, and the k with the k modulus defined as here. And the p's are just polynomials. And if you can take a look here, for a constant density disk, these polynomials are quite simple, but of course, it is more complicated when you want higher orders. Great, but these were disks, let's say elementary disks with the density which just goes up, and reasonable physical disk would requires densities which goes down in the infinity at least. So we need the solution for negative powers in density, and to do this you can use another symmetry of Laplace equation and perform a Kelvin transformation or the inversion with respect to this elementary density rim. It means this kind of transformation, then the potential transformation is this way, and you arrive really with the densities which are negative powers of the radial coordinate and suitable potential in pair. So we can use this and construct some reasonable disks. We construct finite and also infinite disks with possible holes inside. And one particular solution which will be useful here are infinite annular disks. So we are assuming that we have infinite disks, but with finite mass m, that are stretching from some finite radii to infinity and has the density of this form. Then the corresponding potential of this disk is just written in this way, where these pi's are some combination of the polynomials you have seen before, and the tildes means that they are the inverted versions that performing the Kelvin transformation I showed you in the latter screen. Okay, better to show you some pictures. So here on the right side, there are the densities for various exponents in the density, and it is really a disk which starts somewhere and goes to infinity, and the density is falling down relatively quickly. Here on the left side, you can see again the disk, which is this horizontal thick black line with a reasonable density, which is the thick blue line, and the contour plot on the background. It is a contour plot of this potential, and it is, let's say, cartographic. So from the green areas to white areas, it means that the potential is deeper or is bigger. Great, and then we have Laplace equation. Therefore, to do a superposition with a black hole is very easy. You can just sum the contribution from the Schwarzschild black hole and the disk, and you have the force solution. And given the reasonable parameters, for example, in the galactic scales, all these disks are finite, have finite and non-negative density, and also the azimuthal pressure, and satisfies all the energy conditions. And the vacuum space-times everywhere is regular outside the horizon, except the potential problems at the inner edge, where the higher derivatives, but only the higher derivatives of the curvature doesn't has to be regular. Then we can use this full relativistic static superposition and perturb it by a slow rotation. So if we take a look on the equation for the dragging function, for the dragging angular velocity, you can again see that if we assume that the rotation is slow, so we take only the linear order, omega, then this term goes away, and the equation is not dependent on the potential. It's only here. So the dragging can be chosen independently of the potential of the disk, if we assume that the rotation is slow. So we can use the green function and really integrate some solution, but unfortunately, only the constant dragging density with this constant S solution is known analytically, but for more appropriate profile of the dragging density, we have to still use the numerical integration of the green function. And unfortunately, the green function is the expressions are rather long, so I'm not displaying here. I will show you just some numerical results. So now here's the question about the rotational curves. So my question is, can the relativistic dragging in this solution play an important role in the rotational curves? So first we have to make clear what we are measuring and who is performing the measurement. So we assume that the stars are just glide across space-time, so they are following geodesics. That means that their forward velocity, that their forward acceleration of this forward velocity must vanish. So they are performing geodesic orbits. That means that this condition on the angular velocity with plus and minus, that means either the direction co-rotating with the disk or contra-rotating with the disk. As the observer, as the Balazs and Grumier, we choose the zero angular momentum observer, which are really that one whose angular velocity is non-zero, and it is given by this dragging function omega. And now to obtain really a physical speed, what would ZAMO measure, we decompose the forward velocity of the star into the tangential and normal component with respect to the ZAMO observer. That means that this V velocity is orthogonal to the ZAMOs, and this gamma is just the Lorentz factor given by the projection of the forward velocity of the star onto the ZAMO. And then the linear velocity, which would have been measured by ZAMO observer, is just the norm of this forward velocity V. And if you plug the metric inside and use our expansion in the linear order of omega, you arrive at this expression. And as you can see, the velocity, the measured velocity, has two components. One is given just by the static case, just by the disk without any rotation. And the other contribution is dependent on the dragging of the space-time. So to yes, sorry. Okay, so first, to obtain some reasonable parameters, we did the fitting just first for the static case, and then study if the dragging is somehow important. And so what you can see here is the rotational velocities it's a very similar picture as you could see in the presentation by Dr. CROSTA. So this red line is the BG model, that blue line is the standard Milky Way model, and the disk with a black hole model is this purple one. And we use disk whose Newtonian density looks in this way. And as you can see, the plot is relatively nice around the 10 kiloparsecs. And the parameters of the fit are displayed here. And of course, if you take a look on the mass of the what's supposed to be the black hole, it's way too big to be really a black hole inside the galaxy. Instead, we can interpret it as a bulge, because bulge is supposed to be also, let's say, spherically symmetric. So we could, in principle, replace the black hole with some suitable interior solution, which is outside just the Schwarzschild one, to also fix this part of the rotation curve. But now we are interested in how the dragging contributes to this rotational curve. So we take the same parameters and plot some and really numerically integrate the dragging over some reasonable dragging density, and have some numerical results. And the typical dragging contributions looks like this. And as you can see, the scale here is 3 orders magnitude smaller than the rotational than the real velocities, and this is somehow independent regardless of the choice of the dragging density or of the mass density of the different disk. in every our numerical results, the contribution from the dragging was less than 1%. So clearly the dragging here is not strong enough to explain flat rotational curves. And I can provide you a rhetorical question if the second perturbation order might help, because then it also taking account the full self-gravitation of the rotating disk. But it was very difficult to find the linear perturbation, and it is even more difficult, maybe hopeless, to find the second perturbation. So this is probably not the right route. And just a note here, in all the numerical results, the rotation of the disk was chosen to be maximal within the linear perturbation, so that we do not exceed really the linear perturbation. Either, of course, you can make any contribution you can. Okay, that's all from me. I would like to thank you, my supervisor, Professor Semerak, and my colleague David Cockburn for the useful discussions, and also to Dr. Crosta for the hospitality during my stay in Torino. These are some references for you, and I thank you for your attention.
Yes.
Oh, sorry. Yes.
Thank you very much. Very interesting, and we have been collaborating for many years with Professor Semerak. Please bring him my personal regards. But what really concerns me is not the description of the region far away in the disk that you describe. But I think the most delicate point is how to match the disk to a possibility of a Kerr metric. And
sure.
I am especially concerned, if I may use a word, concerned, but I could be even stronger in my statement, of the recent result of the
Even Horizon Telescope.
Of the
Even Horizon Telescope. EHT.
Even Horizon Telescope. Event. The Event Horizon Telescope. There is a lot of discussion about ongoing activity, shadow and so forth in M87. But these people in this time, they want to apply this reasoning to our own galaxy. And to our galactic core. And from this event horizon data, they speak about value of the Kerr metric over M, very large, which could be 7, 8. I think this doesn't make any sense to me. And I would like to have the feedback also of Professor Semerak and yours, because this will disrupt the geodesics going on near the galactic center. And any geodesics which cross by will be disrupted. Therefore, I will be pleased to discuss with you and Semerak about this point. Okay.
Okay, yeah, I think I understand. Okay, but still, I think that especially the dragging of the rotating car, so it goes down quite quickly. So
Yeah.
even though the rotation is very strong of that black hole, so I'm not sure if I would be concerned in the region farther from the black hole in that regard.
Well, it depends, however, for the particle which crosses here and they go back out. This is the problem, because we know that the distribution of matter of the stars around near the galactic center are symmetric to a high degree. Therefore, you are right, the rotation goes down as 1 over r cube, we know. Therefore, if you look at the rest of the galaxy, there is no problem. But the problem is for this poor star which have the occasion to cross by, what will happen?
Okay.
It's not in the disk. Worry. Of course, the disk, you are perfectly right with your approximation. Yes, Mariateresa.
Yes, sorry, I don't find how to raise my hands. So just a comment. So we discussed a lot with Petr many times about the Basel in Grumilla. I perfectly agree that we need more suitable relativistic models. So, okay, but the advantage of Balazin-Grumiller profile, at least for the velocity profile, is that they removed a lot of issues that you mentioned in order to the final form of this an analytical form removed all these issues. I know that this cannot perfectly continue solution from the center to the rest of the galaxy, but it's a selected solution, and it's quite so promising, not the solution itself, but the fact that it represents a first idealized velocity profile with a few parameters, and as you have seen, it fits the data apparently. So the other things that the plot that you show is on the R2 data. Now probably we have to do the same with the R3 data that are much more complicated, so to see. And then be careful, because close to the center there is also the bar, so it's not asymmetric there. So we should be very careful about to select the model. So probably the problem that you add the gravitational dragging as perturbation, not as part of the metric when you performing because we agree all that the basic measurement in general relativity should be the velocity as measured with respect to the local rotating observer. So which kind of piece of geometry or which gave the right profile is still a matter of discussion. But Balazin-Grumiller is a good starting point, at least, I think. At least for this is a solution that has been cut, so it's been removed all the issue that you mentioned at the end. Well, we can agree or not, is not continuous solution, but galaxy is a multi-structure object. You cannot find a globally Einstein solution for the galaxy, I think. That's my comment. Thank you very much, guys. Nice, very nice work, Petr.
Any more questions?
Yes. I would like to make a question.
Yeah, sure.
Yes. So thank you for the talk. Want to know, because in this approach you are trying to let's say mimic the effect of a dark matter component due to the general relativistic distribution of matter in this with this drug. But you have used until now Gaia data of the tracers in the disk. What, as you know, there are independent tracers of the gravitational field of the Milky Way, for example, stellar streams, which goes more at different latitudes and longitudes in galactic coordinates, which I don't know how an axial symmetric solution can account for these different traces, which we know up to now, for example, of the different stellar streams that we need a dark matter component or at least a source of acceleration field at those scales.
Okay, so the sound is not very good, but if I understand your question, so you are asking that the assumption of the axially symmetric galaxy doesn't have to be really a good assumption because you have stars which are moving in the different direction. Is that right? Is that the question?
Yes, due to stellar streams observable.
Oh yeah, of course, that's a good criticism, and of course. I'm not saying that this rotating, slowly rotating disk is really the galaxy itself. I'm just saying that majority of stars might move in the right direction, and that globally that the assumption of the axially symmetric motion is reasonable. But of course, it's the galaxy, the real galaxy will be more complicated. But I think on this global level, it's suitable to assume that the galaxy is really axially symmetric.
Okay,
so that's just my arguing.
Okay, so it's like in this kind of approaches, you will also need a component of dark matter. It's not that you would pretend to completely exclude the paradigm of dark matter, right?
Yes, well, the reason why we tried this was to really see if that dragging can move somehow the rotation velocities. And if it could move them a bit, quite a bit, then it could reduce the necessity of the dark matter around, or at least put another constraint of the amount of dark matter.
I see. Thank you. Yeah.
Okay. Any more questions? If not, let's move to the last speaker of in the morning. Thanks the speaker again. Move to the last speaker.
Hi. Hi. Sorry, but I have a bad sore throat today, unfortunately. I'll try my best.
You intervene.
Okay. So I'm going to show my screen. This one. Okay. So can you see my screen?
Yes, yes.
Okay. So first of all, I think that I really think that the talk about general relativistic model for galaxies that Professor KROSTA and Peter, sorry if I pronounce it wrong, very fits with my presentation. So I don't know why. Okay. So I'm going to talk about the theoretical framework for dust solution. And the references for this talk are this work that I wrote with my supervisor, Professor Cacciatori, and my collaborators, Federico Re. Then I have this other work that I wrote about a generalization of the virial theorem in general relativity, and this other work that we did with Professor Dotti and Professor Ard about the redshift from galaxies. But the presentation is mainly based on this work that I did with Professor Ruggiero, in which we gave a theoretical framework for all dust solution in general relativity. So we are not going to talk about a specific model. It's just this is like a collection of all the possible dust axisymmetric and stationary models for galaxies. So the outline, I'm going to give you the generalities, then the general solution for all possible dust stationary axisymmetric solution in general relativity. Then I'm going to talk about the main limits, so the gravitomagnetic limit and the rigid rotation limit, for which Professor CROSTA talked about, and then I'm going to discuss in general the redshift, and then at the end the virial theorem. The general idea. Okay, I'm not going to the details because my collaborators Federico already did that, and also Professor CROSTA and Peter already did that. But just to sketch, our approach is totally general and applies to all stationary and axisymmetric dust solution. We did not focus on a particular model. So we are going to consider a congruence of particles in the space-time. I'm going to give you on one side the mathematics and on the other side like the physics. So the energy momentum tensor is for dust. Dust, I mean in GR nomenclature, and the system is again stationary and axisymmetric. So we have these two Killing vectors, and as already pointed out before, we wrote the for velocity of the dust in this way, so we can have circular orbits. So now we have a set of coordinates in which we can describe our system. It is very important that the system is confined in a region that is finite, and far from this region, all the fields go fast to zero, and at infinity we have the Minkowski spacetime. Okay, of course we can point out that maybe one should take into account also non-stationary effects, but up to now we focus on this simple kind of simple solution. Weak gravity does not imply Newtonian gravity, and I mean also weak gravity makes sense only in certain configuration. Moreover, we should pay attention to the difference between vacuum and non-vacuum solution, because sometimes people argue that if you take the expansion of 1/c, then you see that all the contribution but the Newtonian are just dumped by a factor 1/c. This is totally wrong, because there is a big difference between vacuum and non-vacuum solution. For example, usually when I try to discuss about it, people tell me that if you take this vector field for the gravitomagnetic field for a galaxy, then you can at least get a rough idea of the gravitomagnetic field of a galaxy. So if you put inside the values of the galaxy, you see that this gravitomagnetic field is negligible compared to the Newtonian field. This is totally wrong, because this is not a solution of solution within the mass distribution, but in vacuum. So we should not confuse vacuum solution and non-vacuum solution. Another example that may be interesting to discuss, let's take about how the distribution of matter can be crucial. We can study the field inside a spherical rotating shell of matter. Inside, the Newtonian potential is 0, but of course, we also have lens steering effect inside. So the distribution of matter is very important. It's not that easy to take the expansion of 1/c when we are inside the distribution, or maybe we have like a shell of matter outside. Again, the full point. So we're not going to discuss a specific model. We are going to discuss the fact that the full application of GR should not be confined to a region where the gravitational field is strong. Like in this case, for this kind of system, axisymmetric and stationary system, a remarkable discrepancy is provided by non-diagonal terms. But in general, we have more terms, because we have certain elements in the metric, but symmetries help us to just fix some elements. But in general, for some object, we can also have much more discrepancies. Okay, let's further discuss general kinematical properties. I'm not going to the details of the mathematics here, just to tell you some rough ideas. So for every congruence of word lines, we can define a deformation tensor that is kind of like like the deformation, so, of course. And then we have the vorticity tensor, that is how much they are kind of rotating. And then we have this acceleration. These three tensors are very important to describe congruence. And we can also build other objects from them that are called the spatial deformation tensor, the spatial vorticity tensor. Okay, of course, the acceleration is already pretty special, and the spatial geometry. What does it mean? It means that you have this deformation tensor that tell you how these word lines are going apart from each other. Then you have the vorticity tensor, that study the vorticity of the fluid, and acceleration. Yes, but to we can project this tensor along the flow of the congruence and in the orthogonal space of the constituents. This is, of course, well known also by the work of Professor Cattaneo. So in the future of this presentation, I'm going to talk about the spatial deformation tensor. That is, okay, we have the congruence, we can define what does it mean, the spatial metric that is orthogonal to the flow of the congruence. Here we can define the spatial deformation tensor that is like the projection orthogonal to the flow. And then we have the vorticity tensor and so on. We can also define the expansion, that is the trace of the deformation tensor, and the shear tensor, that is the off-diagonal terms of the deformation tensor. It is very important because now we can put together all of these ingredients and we can write the covariant derivative of the forward velocity of the field in this way. So to know the kinematical properties, we need the spatial vorticity, the spatial deformation tensor, and then the acceleration. That's it. First result, that is very easy. The fluid motion, of course, is geodesic. So the deformation tensor and the vorticity are totally spatial object. The second result, as Peter already said, is that the fluid motion is expansionless. But this is valid in general, not only for the Balasin-Grumiller or other solution. This is valid. This is totally general. The expansion again is the trace of the deformation tensor. The third result is that the fluid motion is shearless if and only if omega is constant. Omega is the angular velocity as measured from an inertial asymptotic observer. I'm going later to talk about it. So shearless means constant omega. That is why constant omega is called rigid rotation, because the fluid is expansionless and the deformation tensor is 0. Result 4, that has been provided by Professor Cattaneo many years ago. Okay, I'm not going to the details, but just to say that if we have this congruence and then we adapt the observers to this congruence, and then we have a particle going somewhere around this congruence, we can say that the non-inertial forces that we are measuring depend on the spatial vorticity and on the acceleration of the congruence. Okay, I'm going later to talk again about it. So up to now, we discussed the kinematical properties. Again, the fluid is geodesic, is expansionless, and if omega is constant, is shearless. Our model, I mean, is not exactly a model. This is the exact solution for all possible stationary and axisymmetric system with dust source and for velocity written this way along the Killing vectors. This is the full solution. So all the models must be inside the class. All that are discussed must be inside this class. So there is, of course, again, a natural observer called ZAMO that is rotating with angular velocity key. Oh, sorry, there is a typo. The first element must have a plus because h is a negative function and the signature is minus plus 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 plus. Okay, so again, we have this dust that is going around in circular orbits with angular velocity omega. Then we have the ZAMO, that is a zero angular momentum observer that is rotating with angular velocity key as measured from an asymptotic inertial reference frame. But it has, of course, zero angular momentum. So we see that the non-diagonal terms, in the non-diagonal terms, we have the angular velocity of ZAMO in general. The solution depends upon the choice of two dynamical functions. So the system, of course, is not fixed, but we can choose this function h and this function k. If we look at the metric, the first term, we have h, then we have gamma. Gamma is the Lorentz factor respect to the velocity of the ZAMO. So the metric, in fact, in general, is pretty simple because we have a function that we can choose. Then we have gamma. What? Okay. We have h, then we have gamma. And in the non-diagonal terms, again, we have h, gamma, and k. So in general, we can choose h. It's completely, is not fixed, and k. I already talked about the physical interpretation of k, that is the angular velocity of the ZAMO as seen by an asymptotic inertial observer. And now, I didn't talk about the physical interpretation of h yet, but up to now is just a function that we can choose. Once that we choose h and k, we get the model. We may have many different models. Then when you choose h and you choose k, you have to do some derivatives and you completely solve the Einstein equation. It's already solved up to quadratures. This kind of many of these results are by Professor Gayrock and Winnicott in the past. A very important thing is that we have this relation between k, the velocity v, and omega. We see that k is equals to v over r plus gamma square h. So we have a relationship between h, k, and v. In general, omega is not v over r. We see that we have something else, that is the dragging effect. K is like giving a dragging effect in general. Once that you choose h and k, you find the model, and then you can find the density through this equation. Psi is completely fixed again from the equation, and you see from the general solution that it's very easy to have dark matter effects. Okay, I say dark matter effects. What does it mean? It means that here from this term, we have L. L is kind of the logarithmic derivative of H. So if we choose H, we get L, and you see that you can reduce the energy density needed to sustain the motion. So you can, for example, measure V, and then you choose H to fix the energy density. Clearly, here you have dark matter effect. It doesn't mean that you can explain all the dark matter in galaxies. I'm not claiming that you can do it. I'm just claiming that it's easy to provide dark matter effects from geometrical terms. In what sense? In the sense that you can just reduce the density and add geometrical factors in this way. This here is very clear because this is just positive, this is positive, and this is always negative. This is also what I'm going to talk later, how this can be reduced to the Balasin-Gromiller solution, for example. Again, we have to conserve quantities because we have to kill in vectors, we have the energy and the angular momentum. It's very interesting because H and K must depend on R and Z, but actually they only depend on the angular momentum. So their dependence on R and K is totally given by the angular momentum. Galactic redshift. So the question is, what are we actually measuring in general? If I'm far away, let's say I'm an asymptotic observer in the space-time. I look at the galaxy and I want to measure the redshift. I put redshift, I just wrote redshift, but it's of course the light frequency shift due to the just due to the galaxy, not due to the expansion of the universe. So if I just measure the light frequency shift, what am I actually measuring? If the GR effects are negligible, this is only due to the Doppler effect. The theta is just the angle of line of sight. But the exact GR calculation is this one. So in general, this is the result. You see that we have omega, we have h. This is the general result. It's pretty complicated, but if the galaxy is edge on or face on, it becomes pretty simple. Since Federico Re in the last week already talked about it, I'm not going into detail again, but just to mention it, h is the face-on redshift. So we have also the physical interpretation of h. And then in the edge-on case, the result becomes pretty simple again. The photons are emitted from dust in circular geodesics. After the emission, the photons propagate along null geodesics. So that's all, any possible refraction are neglected. The emitted photons is detected by an asymptotic inertial observer. So we know that actually we're measuring them from the Milky Way. So we have to take into account also the gravitational field of the Milky Way. But here you can do it, but you need to use this approach twice. One from the one galaxy to infinity, and then from infinity to our galaxy. But this is just technical fact. The frequency shift is the sum of a Doppler and gravitational contribution. For simplicity, let us consider just an edge-on galaxy. At fifth order, we have this. It's pretty simple, right? So it's just the angular velocity times r. The angular velocity, the relevant result here is that the angular velocity is not v over r. So v, the velocity respect to Zamo, is not the redshift. We are measuring the velocity of the Zamo plus something else. This is relativistic addition of the velocities. This is very important because at some point you can also show that this in general relativity is pretty easy to have a flat velocity profile actually. Okay, since Federico Re already talked about it, about this and going forward, different limits. So we consider the general model, and I say to you that at some point I say to you that if you choose h and k, we can obtain different relevant limits. For example, special relativity, you have to fix h and k in this way. Newtonian case, we have other choices. Then you also have gravitomagnetism, and of course, you never heard about strong gravitomagnetism because it's a recent thing that I discussed in this article with Professor Ruggero, in which you have a stronger version of gravitomagnetism. You see that the key term, now you have a 1 over c, and here you don't have 1 over c, but it's pretty similar. And you can also have the rigid rotating model. That this is, okay, we need to say that is rigid rotating class, because inside the rigid rotating class, you also have the Balasin-Grund-Miller model or the Copperstock and Q model or other models. You need to put h equals to -1 and k equals to this value. Omega is constant. So it's completely rigid rotation model, as we already said, so shearless, expansionless, and the deformation tensor is 0. As Peter already pointed out in the last talk. Again, choosing these values, we can obtain relevant limits, and it's interesting at this point to evaluate the redshift in all these cases. We have for edge-on galaxies again. We have the redshift in the Newtonian case, that is the Doppler effect. In the strong gravitomagnetism, you have also this term, this A are the non-diagonal terms again. So you see that it's fixed A in such a way that you can also have a flat velocity profile. It's pretty easy to do it. Okay, in the rigid rotation, in the rigid rotating case, instead the redshift is always linearly increasing. So as Peter already point out in the last section, we have a different physical problem with the Balazs-Grumiller model, but actually these problems are not due to the model that Balazs and Grumiller choose, but is due to all the class of rigid rotating models. So also the copercent and whatever model you may have if you fix the function in the rigid rotating case, because rigid rotation is a subclass of solution of the general class. So in the case of Balazs and Grumiller, for example, we have linearly increasing redshift as measured from an asymptotic inertial observer. Okay. Okay, let's focus on this case of the case of rigidly rotating model. So it's a class, it's not just Balazs and Grumiller, it's a lot of different class of solution. The rigidly rotating model is a space-time filled with dust rotating with the same angular velocity. So we have omega constant. This is the free velocity of the dust. Even if the angular velocity is constant, this doesn't mean that the velocity v as measured from ZAMO is fixed, because the non-diagonal terms, because you just fix h, you didn't fix key. So you can choose key in such a way that v is not constant. For example, in the, okay, no, I'm not going to discuss it. Again, the deformation tensor is 0, the expansion is 0, the shear is 0, is a general property for all the rigidly rotating models. And another property of all the rigidly rotating models is that the redshift is linearly increasing, and for all the models that are rigidly rotating. So for all the models that have each equal to -1 in our setup. Okay, now a simple rotation, because if you have the free velocity of dust like this, it's pretty easy to do a rotation to write a simple version of the free velocity. So now you are the asymptotic inertial observer. You do a rotation in such a way that you are free falling with dust. If you do this rotation, that is this one, in which you are free falling with dust, you get the metric in this way. That is the one used in the literature. This literature is the metric of a rigidly rotating model described by the word line of congruence with adopted coordinates to the free falling dust. After the rotation, what happened is very nice, because as I show in the article, okay, I'm going to talk about the references later. Now the redshift is 0. What does it mean? You measure the redshift because you're far away and you have this rigidly rotating system. Now you've changed coordinates, you're free falling with dust, and you're not measuring redshift now. Because again, now you're describing the system, you're totally at rest respect to dust. And you get this metric and all the possible models. So if this is a test that I propose in this article is that, for example, if some model inside this rigidly rotating class can describe our galaxy from a theoretical perspective, I know that observation is very complicated and is not that simple, but from a theoretical perspective, this works. If you put ourselves at rest, maybe respect to the sun, we need to measure no redshift from the majority of the other stars in our galaxy, because from the theoretical side, if this metric works, you have no redshift. This is just from the theoretical perspective. Okay, I totally understand that from the observational part, this is pretty complicated. Another way to understand this is that GTT, so the first term in the metric, is always -1 everywhere. Why? This always happen, as Professor Cattaneo showed, when you are describing a word line time-like congruence of a fluid with adapted coordinates to the fluid. So you're flowing with the fluid and you're not accelerating. This is exactly what happened here. The same happened, for example, the Freeman-Robertson-Walker model for the isotropic and homogeneous universe, in which you have the first term that is fixed because you're describing in these coordinates in which you are in these coordinates that are adapted to the fluid. It's nice to, I think, to compare the GR model, the rotating model in GR and the special relativity to see the differences. So we have a rigid rotating model in GR, and then we study the rigid rotation model in special relativity. On the left, you see the GR side, the deformation tensor is 0. But in the special relativity side, only the special part of the deformation tensor is 0. Then I wrote down the metric in the GR case. I wrote down the metric in the special relativistic case. What's the difference? The difference is that it may sound stupid, but I think that is profound. The system in general relativity is held together by gravity, while on special relativity, the system is held together by concrete. So the one in the left is non-accelerating. Okay, now let us imagine that a light signal is emitted from a generic element of the body and it is received from another element of the body. In the GR case, again, we have no redshift. And instead, in the special relativity case, we have this redshift that depends on the point of the emission and the angular velocity of the system. So it's completely different. The cases are very different. Okay, now I'm going to the last part of my talk about new virial theorem. Actually, some possibilities for the virial theorem were already studied by Professor Bonazzola in this article that is called The Virial Theorem in General Relativity. Actually, if you go to the references of this article, you get a lot of different, not a lot, but some papers about it. Recently, I proposed a generalization of the virial theorem for gravitomagnetism. Maybe this can provide an interesting way, I don't know, to test GR effects in a fast way. Let's talk about gravitomagnetism, because the virial theorem that I proposed is in the for the gravitomagnetic limit. Again, to see the importance of our setup, maybe you see that you can fix H and K in this way to get gravitomagnetism. So this virial theorem is a subclass, belong to a subclass of the general solution. Okay, so we have gravitomagnetism. As you know, you have these non-diagonal terms that have a certain order in respect to this expansion in 1/c that is not that important in within the matter distribution. We have the equation for the Newtonian potential as usual. We have also the equation for the gravitomagnetic potential. A nice way to interpret this is to do an analogy with electromagnetism. So we have the gravitational potential, the electric potential that is kind of the Newtonian potential, and then we have the magnetic part, and here is called gravitomagnetic part, and is given by the non-diagonal terms. This is a way to understand it. Of course, there are a lot of differences, but the equations are totally similar. They also share the same gauge transformation. We can define the gravitoelectric field, we can define the gravitomagnetic field, and we have the geodesic equation in the stationary condition at first order in V/c. If we study the equilibrium of an axially symmetric self-gravitational dust fluid, we get this equation. So if you take this metric, put inside the Einstein equation, you get the solution. Or on the other way, you can take the general solution, put inside this choice, and you get the same equation. It's totally is the same thing. You see that in the Newtonian model we have the first equation, but if you add the gravitomagnetic correction, you have another term that is the scalar product between the vorticity and it's like a coupling between the vorticity and magnetic field of the galaxy or whatever you're trying to describe. You see here, there is something that is important. Here, the system is not necessarily axisymmetric. It is just stationary, because here we have a scalar product and we have a full vector A, but you can choose H in such a way that this become axisymmetric. So this is general. This is a weak field in slow motion, and that is also stationary, but not axisymmetric. You see here what happens, something that I told you before. We have this term that we call density correction with respect to the Newtonian model. Let's say we are in the Newtonian case. We measure some velocity v and then we fix rho. But more generally, we have other terms here. In the case of gravitomagnetism, we have this term that we can choose in such a way that we can reduce the density needed to describe the motion. So this is the density correction in the case of gravitomagnetism. You can find the density correction in general, just taking this rho and you subtract the Newtonian density. Actually, all Newtonian axisymmetric stationary system are not physical because they are an infinite cylinders. Everyone knows that. Of course, this is just get you the rough idea that locally we have this discrepancy. Okay, so in the case of gravitomagnetism, you can write this new virial theorem. So we have the kinetic term, we have the potential, and then we have another term that I call H. H depends on A. That again is, you see the non-diagonal terms. So the non-diagonal terms contribute to the virial theorem, contribute to the equation of motion in this way. H looks pretty complicated, but we can actually, it is not. I'm going to show you later that as a beautiful physical interpretation. We have 2K, 2 times the kinetical energy plus the potential energy. I forgot this here, the time long average here. Okay, it's just the usual virial theorem with another term. You see here what happened. You see here happened that you can add non-diagonal terms to reduce the amount of kinetic energy that you need, maybe. So you can reduce the density. Again, you can clearly see it from the virial theorem. It becomes clearer if you rewrite this H, if you do partial integration. I think that the result is very nice because you get this. 2 times the kinetic energy is equal to the integral of a squared plus b squared. If you do the calculation again, okay, for gravitomagnetism, for electromagnetism, this is straightforward. This is the energy stored in the electromagnetic field. But in general relativity, I did all the calculation again from a covariant perspective, and you get that again. This is the energy stored in the gravitational field. I know that it's hard to define what is the gravitational energy stored in a region. But here, I'm going to assume that the galaxy is a compact object in a compact region of the spacetime, and everything is far away. So there is a clear meaning of where is the gravitational field. Again, so the virial theorem becomes pretty simple because it's 2 times the kinetic energy of dust equals energy of gravity. It's clear. It's just there because this is. If you do the calculation, this is the energy stored in the gravitational field. So it took this form. If you don't like this interpretation, this is an exact result at the expansion for gravitomagnetism. This result can reduce the amount of matter needed to sustain a motion with velocity v compared to the Newtonian version of the same theorem. It's not restricted to axisymmetric spacetime. It's only valid for gravitomagnetism. You can do something more general, but for example, for axisymmetric spacetime. but it's very hard to write it down and to take. But Professor Bonazzola took steps in that direction. So I think that this may be tested, and it has a nice interpretation, I hope. I don't know. Conclusion. So we analyze the impact of non-Newtonian effects on gravities. We didn't propose any model. We just studied the general setup, just to say, okay, I don't know, the galaxy is something that is very complicated. We have parts, we have some, okay, it's complicated. And models can have also singularities, and it's hard to interpret the coordinates when we choose some models. But let's say that in general, maybe the dynamic of some galaxies can described by some general relativistic model with these symmetries that are, if you look at them, they are global. If you do this, you see that the geometric effect can reduce the needed amount of matter. And we wrote all the possible solutions. Now, what we say is this, okay, we think that this result is not due to the particular killing vector that we choose. We claim that it may be interesting to study all the objects with even when we are not in presence of strong gravitational field, but in general, with the full power of GR, and we may have the same results. So geometric effect can reduce the needed amount of matter. All of this may be important to reduce the dark matter compared to the Newtonian version for some galaxies. So that's why I called all the work reweighting dark matter in galaxies. I'm not claiming that this can, up to now, that this can describe dark matter everywhere. No, I'm not saying this. I'm saying, look, we need to take general relativity seriously. That's it. Okay, this is also, thank you.
Okay, thanks. The interesting talk. Any questions?
Hello. Yes, I would like to make a question. I'm Carlos Reyes. Thank you, Davide. Have you, did you make any estimate of the reduced amount of dark matter that you may need, for example, for a given this galaxy, that you have a nice rotation curve that you can make these constraints, a number?
Okay, that's the point. Since we didn't choose any model, we were not able to do that. But this, of course, as you point out, this is very, very important. This is the next step. But in this direction, already Professor CROSTA and Peter already tried to do that. So they choose a subclass of solution. They took the solution and tried to apply. I think that it's very hard to find a particular model to describe the galaxy. But at some point, we should do it. Maybe we can find a model that can capture the main dynamics on the galaxy, and we can add some perturbation. So the work of, I think that is the work of Peter may be interesting in general, not just the model that they choose. But yes, you're right. We didn't do it yet. Short answer.
Okay, thank you. Yeah. Okay.
May I do another comment? Thank you, Davide. Very interesting talk. So what I understood that you are going in the same direction that we took with the first test. Since apart from the Balasin-Miller model, so we know that there is Gaia data, for example, the Gaia observer is attached such a congruence of curve with respect to which you can define the kinematical property of the star according to GR, not according to Newtonian sense. That I think that the common, now we have the definition of the spatial velocity in this context is quite different from Newtonian one at first. Then when you show that the H is equal 1 to Balasin-Miller, this for the reason that in Balasin-Miller, when they found this analytical solution that had some limitation, but at least it works because apparently it fit data. So we should understand why. If it is wrong, why does it fit the data? But this solution is analytically consistent with a limited part of the equatorial plane for small zeta, of course, zeta equals 0, not close, of course, very far from the galactic center. But this, of course, when the 0 term is equal to -1, this means that in your normalization factor is the minimum. So it means that you are measuring only gravitational dragging. And this is why I think that this should be the main concept that should emerge from this. Then, of course, we need to solve Einstein equation, because to fit the model, we need also to have some, for example, the advantage of Balasin and Miller that they give us a velocity profile. So in your equation, I don't see a real velocity profile, which depends on some parameter that we can fit, or some characteristic feature of the galaxy, for example, as the BG model, because the BG model predict, okay, with the R3 data, we are see there are different other things, for example, that I didn't mention in my talk, when we did the fit, for the relativistic model, we use uniform prior, because we don't have any value. And even though we're using uniform prior, we get a nice result. Now with the DR3 data, we are still using uniform prior. And of course, these parameters change a little bit according to your sample. So this is a very important part of the problem, also to have something that we can match with the data of Gaia, that we can test with Gaia data.
Okay. Yes, I think you're totally right. All the observational part is pretty complicated, and just to say, I can just my presentation. I can describe it in a short way like this. Okay, what you're doing is pretty pretty important, because from the general perspective, you see that this may happen. I don't know about the particular model that you choose, and the particular model may be complicated. As you point out, I don't have a velocity profile. I'm just saying, I think that this could be important from a general perspective. And the model is just a something technical that we need to found, but this may be important in some way.
Okay, thank you.
Thank you.
Thank you.
Thank you.
Okay. Any more questions?
Maybe I might have, thank you for the talk, Davide. I might have just maybe philosophical questions.
Yes.
Do you think that there will really be some dust solution without problems? Because I'm starting more and more to believe that every dust solution will have some kind of singularity somewhere which presents the dust to fall in and stuff like that, or like in the Balasin and Grumiller, that there will be something rotating which brings the rotation to the space-time. So if you think that there will be any model without any singularities or other issues.
I thank you for the question. I did the exact same question to my collaborator like 1 month ago. Same question, like we will ever find a model that is physical, like also singularities. You were talking about singularities, but I'm always also concerned about the asymptotic profile. So like, can we find an asymptotic profile that goes to Minkowski, or we need to say, okay, let's cut the solution and join the vacuum solution? These are two different approaches. And there are some theorems about how to join the internal part with the external part. I'm starting to look at them, but I mean, I don't know the answer actually. I'm just trying to figure it out, but it looks hard. I don't know. So maybe you figure it out and you can explain it.
So you are suggesting move the unphysicalities to the infinity, basically, which can be done by some transformation usually, and then just cut a region and match the interior solution with some exterior solution.
Yes, this may work, but this is totally physical. So you can choose like a solution in a region, and then if you're able to glue in the solution in such a way that doesn't break the Einstein equation, this is physical. I mean, it's totally physical.
Okay, thank you.
So thank you for the questions.
Any more questions? Okay, if not, thanks the speaker kings. Also thanks to all the speaker in the morning. We can stop here in the morning session. In the afternoon, we discuss starting at 3 o'clock. Okay, bye-bye.
Bye, thank you.
Bye, thank you all.
Bye, thank you.